The comet crosses Neptune's orbit on a Tuesday morning in February, though Tuesday means nothing to the ice, and morning exists only on Earth. Out here, at 30 astronomical units from the Sun, light takes 4 hours to arrive, already old, already tired. The comet itself is older still, formed perhaps 4.5 billion years ago in a protoplanetary disk orbiting a star that may no longer exist, a star whose light has not yet reached our telescopes, may never reach them. It carries ice that condensed when Earth was still a scatter of dust grains circling an infant sun. The comet does not announce itself. It simply continues. As it has continued for millennia, perhaps millions of years, moving through the space between stars at 26 kilometers per second relative to the Sun. This is faster than anything bound to our solar system travels, faster than the planets in their elliptical patience, faster than the comets that return, century after century, locked in orbital memory. This velocity is the signature of elsewhere, of gravitational allegiance to a different center, now abandoned or escaped. No sound accompanies its passage. Space offers no medium for compression waves, no air to carry vibration. The comet moves in perfect silence, trailing a coma of sublimated gas that spreads for tens of thousands of kilometers in every direction: water vapor, carbon monoxide, carbon dioxide, molecular fragments, all glowing faintly as solar ultraviolet ionizes them, strips electrons, makes them visible. But visible is a generous word. The comet's magnitude at discovery is 19, which means it appears roughly 200,000 times dimmer than the faintest star the human eye can perceive. Only took 4 billion years to arrive, and still too faint to see without machines. The nucleus itself measures perhaps 1 kilometer across, though uncertainty wraps this estimate. No spacecraft will visit, no probe will land. The comet's trajectory carries it through the inner solar system only once. A parabola so extreme it becomes hyperbolic, a curve that never closes. Astronomers calculate its orbital eccentricity at approximately 1.4, which in the mathematics of celestial mechanics means unbound, departing, never returning. The Sun's gravity bends its path but cannot capture it. After perihelion, closest approach to the Sun, the comet will simply continue outward, velocity increasing as it falls up the gravity well, climbing back toward interstellar space at a leisurely 20 kilometers per second, which will feel like stillness across the light years. Behind it, in the wake of its passage, the comet leaves a trail, not a tail, that comes later, pushed by solar radiation, but a corridor of particles shed continuously as the nucleus rotates and sublimates, losing mass with each moment closer to the Sun. These particles are micrometeoroids, most smaller than grains of sand, many the size of smoke particles, fragments of ice and silicate and carbonaceous material that once formed part of the comet's body. They separate gently, nudged away by outgassing jets, by the faint pressure of sublimation, by radiation pushing against their tiny cross-sections. Each particle inherits the comet's trajectory, its velocity, its hyperbolic fate, but each also diverges slightly, perturbed by the pressure of light, by its own mass and composition, by the particular moment and angle of its release. The corridor they form is not visible, not distinct. It exists only in orbital space, in the mathematical abstraction of trajectories plotted through 6-dimensional phase space. Position and velocity, integrated forward through time under the influence of the Sun's gravity, the planet's small tugs. The Yarkovsky effect as absorbed sunlight re-radiates asymmetrically. Each micrometeoroid becomes its own tiny world, following its own path, though the paths remain close enough, similar enough, to form a stream, a region of space where particle density increases, where the probability of encounter rises from nearly zero to merely improbable. The comet itself remains unaware. It possesses no consciousness, no sensory apparatus, no capacity for observation. It does not know it came from interstellar space, does not know it is being watched, photographed, analyzed through the spectroscopic decomposition of its reflected and emitted light, does not know that the molecules sublimating from its surface are being compared to comets born in this solar system, to the chemical signatures of our own formation. The comet simply continues its response to gravity, to solar heating, to the physical laws that have governed its existence since condensation. Astronomers assign it a designation, 3I/Atlas. The 3I marks it as the third confirmed interstellar object, after 1I/Oumuamua, which tumbled through in 2017, and 2I/Borisov, which passed in 2019. The Tailless indicates its discovery by the Asteroid Terrestrial Impact Last Alert System, a network of telescopes designed to find objects that might threaten Earth. Though this comet poses no threat, its closest approach to Earth is measured in astronomical units, millions of kilometers, a distance that renders collision not merely unlikely, but geometrically impossible given the trajectories involved. Still, the system watches, catalogs, calculates. Only took humans 400 years of telescopy to develop automated surveys capable of detecting faint interstellar visitors. The comet, meanwhile, took possibly millions of years to arrive, and does not notice either the watching or the calculation. The discovery images show a faint smudge against the background stars, barely distinguishable from cosmic ray hits and detector noise. Confirmation requires multiple nights of observation, watching the smudge move against the fixed stars at a rate and direction inconsistent with asteroids or comets of the inner solar system. The motion is too fast, the angle wrong. Further observation provides enough positions to calculate a preliminary orbit, and the orbit reveals the truth: hyperbolic eccentricity, excessive velocity, origin from the direction of the constellation Ursa Major, though constellation means nothing in 3 dimensions, Ursa Major being merely a chance alignment of stars at vastly different distances, and the comet's approach vector only coincidentally pointing back toward that region of sky. What remains mysterious is where exactly the comet formed. Ursa Major contains hundreds of stars within the volume of space from which the comet might have been ejected, and the comet's travel time could span anywhere from 1 to 10 million years, depending on when and how it was expelled from its birth system. 10 million years ago, those stars occupied different positions. The galaxy rotates. Stars orbit the galactic center at different speeds depending on their distance from the core. Tracing the comet's path backward through time requires not only knowing its current velocity precisely, but also accounting for perturbations from every star it passed during its journey. Gravitational nudges too subtle to reconstruct without knowing the comet's exact route through the local stellar neighborhood. The corridor of its past remains uncertain, erasable, only took 10 million years, perhaps to cross the light years, and no way now to know which star expelled it, which planetary system formed and failed to keep it. The comet carries no signature of its origin beyond the chemical composition of its ice, and ice from different stellar systems may not differ enough to distinguish. The ratios of isotopes, deuterium to hydrogen, carbon-13 to carbon-12, nitrogen-15 to nitrogen-14, provide hints about formation temperature, about the local environment in the protoplanetary disk where the ice condensed. But these ratios overlap. These ranges blur between systems. What the comet remembers, it remembers involatiles and silicates, and these memories do not speak clearly. The corridor continues forming. Behind the comet, in the curved wake of its passage, micrometeoroids drift. Some will eventually intersect Earth's orbit, though not for centuries, perhaps millennia. When they do, they will enter the atmosphere at speeds exceeding 70 kilometers per second, the combination of Earth's orbital velocity and their own hyperbolic excess, they will heat, ionize, ablate, vanish in streaks of light lasting fractions of a second. To any observer, they will appear identical to ordinary meteors, to the dust shed by solar system comets, to the background flux of particles that burns constantly in the upper atmosphere. Only orbital calculations performed after the fact, tracking back through the geometry of their arrival, might reveal their interstellar origin. Most will go untracked. Most will simply burn, uncatalogued, contributing their atoms to the mesosphere. The comet, meanwhile, continues inward, still beyond Neptune, still in the realm where the sun appears merely as the brightest star. It sublimates slowly, losing mass at a rate measured in kilograms per second, which sounds substantial until compared to its total mass of trillions of kilograms, a loss rate that would take millions of years to consume the nucleus entirely. But it will not remain in sunlight for millions of years, only a few months, perhaps a year, close enough for heating, then departure, return to the cold. The corridor trails behind, silent and geometric, defined by particles too small to see, too dispersed to photograph. It exists. The mathematics insist. The physics require it. But to look is to see nothing, only darkness, only the unchanged field of background stars. Only took 1 billion years for the comet's birth star to produce planets, to scatter some beyond recovery. And here, now is the evidence. Invisible. Drifting. The naming happens in offices and observatories scattered across Earth's surface, in hemispheres experiencing different seasons, different times of day. Astronomers in Hawaii submit the discovery report. Astronomers in Chile confirm the observations. Astronomers in Arizona calculate preliminary orbital elements. The comet does not participate in this process, continues its trajectory regardless of designation, indifferent to the alphabetic and numeric symbols humans assign to distinguish it from other small bodies moving through the dark. The provisional designation comes first. CC 2024 S3, where C indicates comet. 2024 marks the year of discovery. It denotes the half-month of September, and 3 shows it is the third comet discovered in that period. This label is temporary, bureaucratic, a placeholder until enough observations accumulate to determine whether the orbit is secure, whether the object merits permanent cataloging. For weeks, the comet travels under this designation while telescopes around the world gather photometric data, astrometric positions, spectroscopic measurements of the light reflected and emitted from its growing coma. The Atlas system that discovered it, Asteroid Terrestrial Impact Last Alert System, operates 4 telescopes, 2 in Hawaii, 1 in Chile, 1 in South Africa. Each telescope surveys the entire visible sky every 2 nights, comparing images to detect moving objects, transient events, anything that changes against the supposedly fixed background of distant stars and galaxies. The system was designed primarily for planetary defense, for finding asteroids whose orbits might intersect Earth's, objects that might require deflection or at minimum advance warning. But the system is democratic in its detection. It finds asteroids, comets, supernovae, variable stars, whatever moves or brightens or changes. The comet triggered the detection algorithm simply by existing, by reflecting enough sunlight to register on the digital sensors, by moving at a rate consistent with solar system membership, though, ironically, it is not a member, merely a visitor, temporary and unbound. Only took decades of algorithm development to automate the detection process. And still, human observers must verify, must distinguish real objects from cosmic ray hits, from hot pixels, from artifacts of image processing. The verification happens quickly for this object. The motion is clear, consistent across multiple frames. Other observers confirm it within days. The Minor Planet Center receives the reports, assigns the provisional designation, publishes the discovery in its electronic circular, the Comet. 30 astronomical units from Earth, continues sublimating, unaware that it has been officially noticed. When the orbital calculations reveal hyperbolic eccentricity, when the trajectory proves unbound, the designation changes. The Minor Planet Center consults with the International Astronomical Union, with the Working Group for Small Body Nomenclature, with various committees responsible for maintaining order in the naming of celestial objects. Interstellar objects require special designation, different from periodic comets, different from long-period comets, different from asteroids. The prefix changes from C/ to I/, where I indicates interstellar. The suffix changes to include the discovery system, Tailless. The number prefix indicates sequence, 3I, the third confirmed interstellar object ever detected. Thus, 3I/Atlas, 4 characters, a slash, 5 more characters. 10 symbols to identify an object that existed for billions of years without needing identification. That crossed light years without requiring a name. That will continue into the dark long after human civilization has ended, after Earth's biosphere has been sterilized by the sun's eventual expansion into a red giant, after the sun itself has collapsed into a white dwarf, cooling slowly toward absolute zero. The name will outlast its speakers by perhaps a few thousand years, preserved in astronomical databases until the databases decay, until the storage media fail, until no machines remain to read the designations. The comet will still exist, still move, carrying its ice towards some distant encounter with another star's gravitational field, millions of years hence, in a galaxy rotated to unrecognizable configuration. What remains uncertain about the naming is whether this is truly the third interstellar object detected or merely the third confirmed. Detection bias affects the count. Small. Faint objects passing through the outer solar system escape notice unless they happen to cross a telescope's field of view during a survey, unless they brighten enough to register, unless their motion is obvious enough to trigger detection algorithms. How many interstellar visitors have passed undetected? The question cannot be answered with certainty. Statistical models suggest perhaps one interstellar object larger than 100 meters crosses the inner solar system per year, but most would appear stellar. Point sources. No obvious motion during brief observations. Lost among the background stars. Only took Oumuamua's unusual brightness variation and rapid motion to make its interstellar nature obvious. Only took Borisov's clear cometary activity, coma, tail outgassing, to confirm its extrasolar origin. Atlas presents more subtly, fainter, less active, requiring careful orbital analysis to distinguish from extremely long-period comets whose aphelia lie in the Oort cloud. The Oort cloud complicates the distinction. This vast spherical shell of icy bodies surrounds the solar system, extending from several thousand astronomical units to perhaps 100,000 astronomical units, nearly halfway to the nearest star. Comets originating in the Oort cloud can have orbital periods measured in millions of years, eccentricities approaching but not exceeding unity, velocities at perihelion that appear rapid but remain gravitationally bound. An object on its first passage from the Oort cloud might resemble an interstellar visitor in velocity and trajectory, distinguishable only through precise orbital calculation, through measuring the eccentricity to sufficient decimal places to determine whether it exceeds 1. Atlas's eccentricity is measured at approximately 1.4, clearly hyperbolic, clearly unbound, but early observations, with fewer data points, with larger uncertainties, showed eccentricities that might have been 0.99 or 1. 0.1, ambiguous, requiring weeks of additional observation to resolve. The naming waited for this resolution. For certainty, the comet itself offers no opinion on its designation. It has no capacity for opinion, no neurology, No information processing beyond the mechanical response of its constituent molecules to electromagnetic radiation and gravitational fields. When solar photons strike its surface, the ice absorbs infrared wavelengths, warms, sublimates. This is not sensation. This is thermodynamics. When the vapor expands outward, carrying dust particles into the coma, this is not exhalation. This is pressure gradient. The comet does not experience its own activity, does not notice the slow erosion of its nucleus, does not anticipate perihelion or remember its formation. It exists in the eternal present of non-consciousness, governed entirely by physics, responding to forces without awareness of response. Humans, meanwhile, compose press releases. The discovery of an interstellar comet warrants public announcement, educational outreach, popular science articles explaining what interstellar means, how rare such detections are, what scientists hope to learn from studying an object formed around another star. The press releases emphasize the exotic origin, the billions of years of travel, the opportunity to analyze material from beyond our solar system without requiring interstellar travel. They include artists' illustrations of the comet. Though no actual images resolve the nucleus, the comet appears in photographs only as a diffuse blur, a faint elongated smudge representing the unresolved coma. The illustrations show a rocky, icy nucleus surrounded by glowing gas, a stylized tail streaming behind, stars scattered in the background. These images are essentially fiction, informed guesses based on other comets, on theoretical models, on aesthetic conventions for depicting space objects. The true appearance of the comet, what it would look like to an observer floating beside it, seeing it with human eyes rather than digital sensors, remains unknown. Unknowable without sending a spacecraft, which will not happen. Only took 400 years of astronomical observation to detect 3 interstellar objects with certainty, and already the naming conventions are evolving, the procedures for verification are improving, the statistical understanding of interstellar object frequency is sharpening. In another century, perhaps interstellar visitors will be detected weekly, catalogued routinely, their trajectories and compositions added to growing databases mapping the chemical diversity of stellar systems within the local galactic neighborhood. Or perhaps detection rates will remain low. Perhaps most interstellar objects will continue passing unnoticed. Perhaps the 3 confirmed examples represent unusual cases, larger, brighter, better timed to cross Earth's orbital plane when telescopes happen to be watching. The corridor of uncertainty extends in both directions, toward past visitors undetected and future visitors not yet arrived. The name Atlas, meanwhile, derives not from the Greek Titan condemned to hold the celestial sphere, though the coincidence is noted in several press releases. Atlas is simply an acronym. Already mentioned, Asteroid Terrestrial Impact Last Alert System. The system itself was named somewhat playfully. The acronym constructed to reference the mythological figure, though the connection is thematic rather than functional. Atlas holding up the sky. The telescope system watching the sky for threats. This kind of naming is common in astronomy, backronyms, mythological references, names chosen for euphony or cultural resonance rather than descriptive accuracy. The comet inherits this playfulness without participating in it, without being playful, being merely ice and rock moving through vacuum under gravitational influence. What the name does not capture is the comet's origin star. Because the origin star is unknown, no spectrographic signature definitively identifies the parent system. No trajectory calculation traces back with enough precision through the gravitational perturbations of the last several million years to pinpoint a source. The comet came from somewhere, but somewhere remains vague. A region of sky roughly corresponding to Ursa Major. But Ursa Major contains hundreds of candidate stars within reasonable ejection distance, and reasonable spans a wide range depending on assumed travel time and ejection velocity. The name Atlas identifies the discovery system, not the origin. The comet carries no passport, no isotopic signature unique enough to determine birthplace. It is anonymous ice, identified only by when and where humans happen to notice it. The corridor of micrometeoroids trailing behind inherits no name at all. Micrometeoroid streams are rarely named unless they produce observable meteor showers when Earth intersects their orbit, and Earth will not intersect this stream for centuries at minimum, possibly millennia. Possibly never if planetary perturbations shift the stream's geometry sufficiently. The particles drift unnamed, uncatalogued individually, too numerous and small to track. They exist as a statistical phenomenon, a region of enhanced particle density, a corridor defined by shared orbital elements, semi-major axis, eccentricity, inclination, argument of perihelion, longitude of ascending node, all clustering within narrow ranges that identify them as siblings. Fragments of the same parent body. To name them would require naming millions of particles, each on its own unique trajectory. Instead, they remain anonymous, identified only by their parent, the Atlas stream, the Atlas meteoroid complex, the debris trail of 3E/Atlas, collective designation for individual objects, each smaller than a grain of sand, each alone in darkness. Only took 10 characters to name the comet, and infinite silence to contain the particles it sheds. What makes a comet interstellar is velocity, not origin, though origin determines velocity, and velocity reveals origin. The distinction matters in the mathematics. An object formed in this solar system, no matter how distant its current position, no matter how extreme its orbital eccentricity, remains gravitationally bound to the Sun. Its total orbital energy, the sum of kinetic energy and gravitational potential energy, is negative. This negative value means captured, means the object cannot escape without additional acceleration, means it will eventually fall back toward the Sun, completing an orbit even if that orbit requires millions of years. An interstellar object possesses positive total orbital energy. Its kinetic energy exceeds the magnitude of its gravitational potential energy at any given distance from the Sun. This excess energy translates into velocity, specifically hyperbolic excess velocity, the speed remaining after escaping the Sun's gravitational influence entirely, for 3I/Atlas. This excess is approximately 26 kilometers per second, measured relative to the local standard of rest. The reference frame defined by the average motion of stars in the solar neighborhood, 26 kilometers per second, is modest for interstellar space, slower than many stars orbit the galactic center, but sufficient to ensure the comet will never return. Will coast outward until perturbed by another star's gravity millions of years hence. The calculation of this velocity requires precise measurement of the comet's position over time, fitting these positions to orbital models, solving for the 6 orbital elements that define the comet's path through 3-dimensional space. The measurements themselves come from astrometry, determining the comet's location against the background stars to sub-arc-second precision, photographing it on multiple nights, tracking its motion across the sky. Each observation provides 2 coordinates, right ascension and declination, celestial equivalents of longitude and latitude. Multiple observations across weeks or months allow astronomers to determine not just position but velocity, not just apparent motion across the sky but actual trajectory through space. The orbital elements derived from these observations include eccentricity, which for 3I/Atlas exceeds unity, approximately 1.4, indicating a hyperbolic orbit. This value carries uncertainty. Measurements list it as 1.4 plus or minus 0. On, a range that reflects noise in the observations, atmospheric distortion, the finite precision of telescopes and detectors, but even the lower bound of this range, 1.3, remains comfortably hyperbolic, comfortably unbound. Only took decades of improved astrometric technique to reduce uncertainties to levels where hyperbolic eccentricities can be confidently distinguished from near parabolic eccentricities approaching unity from below. Earlier observations, with larger error bars, might have left the question ambiguous for months. What remains mysterious is how the comet achieved this hyperbolic trajectory. What mechanism expelled it from its birth system at sufficient velocity to escape not only the parent star's gravity, but also the gravity of any planets that might have perturbed it? Several scenarios seem plausible. A close encounter with a giant planet, a Jupiter or Saturn analog, could gravitationally slingshot a comet outward, accelerating it beyond escape velocity through the same orbital mechanics that spacecraft use for gravity assists. Alternatively, a stellar encounter, two stars passing within a few thousand astronomical units of each other, might disrupt the outer cometary reservoir of one system, flinging objects into interstellar space through tidal perturbation. Or the comet might have formed in a system with multiple stars, orbiting in complex gravitational landscapes where three-body interactions occasionally eject objects to infinity. Each mechanism predicts slightly different outcomes, different velocity distributions, different ejection rates. Single-star systems with massive outer planets should eject comets at lower average velocities, typically 10 to 30 kilometers per second relative to the parent star. Multi-star systems generate higher velocity ejections through more violent encounters, sometimes exceeding 50 kilometers per second. Close stellar passages can impart even higher velocities to objects in the outer edges of affected systems. The comet's observed velocity, 26 kilometers per second, fits comfortably within the range predicted for giant planet ejection, suggesting it may have originated in a system similar to our own, with outer gas giants capable of scattering comets during the late stages of planetary formation. But the comet itself carries no record of this ejection, no memory encoded in its structure. The ice that forms its nucleus condensed billions of years ago in the protoplanetary disk of its birth star, accreting slowly from smaller grains, growing through gentle collisions in the cold outer regions where volatile compounds remained solid. The process resembled planetary formation in our own solar system. Dust grains colliding, sticking through electrostatic forces and molecular bonding, accumulating into pebbles, then boulders, then kilometer-scale bodies. The comet represents arrested development, a planetesimal that never accreted into a planet, never grew beyond this intermediate stage. Most such objects remained in their birth systems, populating Kuiper belt analogs or Oort cloud analogs around their parent stars. This one was expelled. The expulsion itself likely occurred early, during the first few 100 million years of the system's existence, when planetary migration was common, when giant planets still wandered inward or outward through gravitational interactions with remaining planetesimals and with each other. This migration scattered smaller bodies throughout the system, ejecting some to interstellar space, capturing others into stable outer reservoirs, occasionally flinging objects inward where they might impact terrestrial planets still forming. The comet survived this chaos by escaping it, by achieving sufficient velocity to leave the system entirely, by beginning its long drift through the galaxy. Only took a few orbits around the parent star, perhaps before the close encounter that ejected it, decades or centuries of normal cometary existence, orbiting peacefully in the outer system, followed by one unlucky passage too close to a migrating giant planet. The gravitational interaction would have lasted only hours or days, bending the comet's trajectory from elliptical to hyperbolic, accelerating it from bound to unbound. No sudden impact, no violent collision, just the smooth warping of space-time by mass, redirecting momentum through the geometry of orbital mechanics, and then departure, velocity increasing as the comet climbed up the gravity well, leaving the planetary system behind, entering the sparse interstellar medium. The trajectory that resulted is not random. It points back, roughly, toward the comet's direction of arrival, toward Ursa Major. But this direction reflects galactic rotation as much as ejection geometry. The galaxy rotates differentially, inner regions completing orbits faster than outer regions, and stars move independently through this rotation, their individual velocities combining orbital motion around the galactic center with peculiar velocities acquired through gravitational interactions with other stars, with giant molecular clouds, with density waves in the galactic disk. The comet's trajectory through this complex gravitational landscape has been affected by every massive object it passed during its journey, nudged slightly by stars it approached within a few light years, perturbed minimally by giant molecular clouds encountered in its path. Reconstructing this path backward requires knowing the comet's velocity vector precisely, not just its speed but its direction in 3 dimensions, and also requires knowing the positions and velocities of all massive objects it might have encountered. The precision required exceeds current observational capabilities. Uncertainties in the comet's velocity amount to several kilometers per second, which over millions of years of travel translates into uncertainties of light years in position, enough to make identifying the origin star impossible among dozens of candidates. Only took 4 billion years for the comet to arrive here, and no way to determine exactly where here began. What the hyperbolic trajectory does reveal with certainty is that the comet formed elsewhere, that the solar system is not its gravitational home, that its appearance here represents a transient visit rather than permanent residence. This certainty comes from mathematics, from the inescapable relationship between velocity and orbital energy, from the physics that govern motion under inverse square forces. The calculations admit no ambiguity. Positive orbital energy means unbound, means interstellar, means visitor. The comet might have been captured if it had arrived more slowly, if its excess velocity had been only a few kilometers per second, if it had encountered Jupiter or Saturn at the right angle and distance to shed enough energy through gravitational interaction. But at 26 kilometers per second excess, capture is impossible. The planets are too small, their gravity too weak, the encounter geometries insufficiently favorable. So the comet passes through, it approaches perihelion, makes its closest pass by the Sun, then departs. Trajectory bent but unbound, velocity at infinity unchanged. The hyperbola is permanent. The corridor it forms is a one-way passage, a geometric trace of an object that came from elsewhere and will never return, carrying ice that condensed in another system's ancient disk, now sublimating in this system's temporary warmth before returning to interstellar cold. Only took precise orbital mechanics to prove where the comet didn't form, even if where it did form remains uncertain. Scattered across light years of possibility, the mathematics themselves are elegant, classical, unchanged since Newton derived them from his laws of motion and gravitation. Kepler's laws describe elliptical orbits. Newton's laws extend them to include parabolic and hyperbolic trajectories. The equations are the same whether the central mass is the Sun, another star, or a galactic core. Gravity does not distinguish between local and foreign objects. It acts equally on all mass, bending trajectories through space-time regardless of origin. The comet experiences the Sun's gravity exactly as a native comet would, follows exactly the same orbital mechanics, sublimates according to exactly the same physics. Only the initial conditions differ, the velocity at which it arrived, the trajectory it followed, the gravitational history that brought it here. And now that history continues forward, the hyperbola extending, the corridor forming, micrometeoroids dispersing behind in a trail that will itself remain hyperbolic, each particle on its own escape trajectory, each carrying a fraction of the comet's excess velocity, each guaranteed to leave the solar system eventually, rejoining the sparse dust of interstellar space. Only took one close encounter billions of years ago to set all this in motion, and nothing now can stop it. The mathematics insist. The trajectory continues. The escape is permanent. The composition of extrasolar ice reveals itself through light, specifically through the absorption and emission lines that appear when molecules interact with electromagnetic radiation. As sunlight reflects off the comet's coma, as ultraviolet radiation ionizes the sublimated gases, each molecular species absorbs and emits photons at characteristic wavelengths determined by quantum mechanical energy levels. Spectroscopy captures this light, dispersing it through diffraction gratings or prisms, spreading the rainbow into a spectrum where bright emission lines and dark absorption lines mark the presence of specific compounds. For 3I/Atlas, spectroscopic observations detect water vapor, hydrogen and oxygen bonded in H2O molecules, the most abundant volatile in comets generally, native or interstellar. The detection comes through emission lines in the ultraviolet and infrared, wavelengths where water's vibrational and rotational transitions produce clear signatures. The abundance is difficult to quantify precisely. Measuring absolute quantities requires knowing the coma's size, density, temperature, but relative abundance can be estimated by comparing water lines to lines from other species. Water dominates, as expected for an icy body formed in the cold outer regions of a protoplanetary disk where water ice remains stable. Carbon monoxide appears in the spectrum as well, identified by its rotational emission lines in the millimeter wavelengths observable by radio telescopes. CO is volatile, sublimating at lower temperatures than water ice, suggesting the comet's nucleus contains regions or layers where carbon monoxide ice remains trapped, preserved since formation. The ratio of carbon monoxide to water, approximately 10% by number of molecules, falls within the range observed for solar system comets, particularly those believed to have formed in the outer regions beyond Neptune, where temperatures allowed CO to condense alongside water. This similarity suggests formation conditions not drastically different from those in our own protoplanetary disk. Similar distances from the parent star, similar temperatures, similar timescales for accumulation. Carbon dioxide also appears, detected through infrared emission bands characteristic of CO2's asymmetric stretch and bending modes, like carbon monoxide. Carbon dioxide is a common cometary volatile, formed when carbon and oxygen atoms combine in cold environments. Its presence indicates the comet formed in a region with sufficient carbon and oxygen abundances, which in turn suggests the parent star had metallicity, elements heavier than hydrogen and helium, comparable to the Sun's metallicity. Stars with very low metallicity, formed early in galactic history from primordial gas dominated by hydrogen and helium, would produce planets and comets with different compositions. Lacking the heavy elements necessary for rocky cores and carbon-rich ices, hydrogen cyanide shows up in some observations, though faintly. At the edge of detectability, HCN forms in protoplanetary disks through complex chemistry involving nitrogen, carbon, and hydrogen, processes that require specific conditions of temperature, pressure, and ultraviolet exposure. Its presence suggests active chemistry in the comet's parent disk. Reactions beyond simple condensation of gas phase molecules onto grain surfaces only took millions of years of disk chemistry to produce the molecular inventory now sublimating away, and the inventory resembles closely what our own comets carry, what formed in our own disk 4.5 billion years ago when the Sun was young and still surrounded by infalling material. What remains mysterious is whether these similarities reflect universal processes, chemistry that occurs the same way in all protoplanetary disks, regardless of location, or whether they indicate coincidentally similar formation environments. Do all solar-type stars produce comets with roughly 10% carbon monoxide, 2% carbon dioxide, trace hydrogen cyanide, or did this comet's parent star happen to resemble the Sun in mass? Luminosity, metallicity, producing conditions essentially identical to those in our early solar system? The sample size is insufficient to answer. 3 confirmed interstellar objects, only 2 analyzed spectroscopically in detail, too few to establish patterns or identify variations. The isotopic ratios provide additional clues, but also additional questions. Deuterium to hydrogen ratio in the water vapor, the abundance of heavy hydrogen relative to normal hydrogen, can be measured through spectroscopic comparison of HDO and H2O emission lines. Deuterium formed in the Big Bang but is destroyed in stellar interiors. Its abundance in protoplanetary disks depends on how much deuterium was present in the molecular cloud from which the star formed, modified by chemical fractionation processes that preferentially incorporate deuterium into certain molecules. The DH ratio in 3I/Atlas water appears similar to solar system comets, roughly 3 times the protosolar value, suggesting similar fractionation processes, similar disk chemistry, similar formation temperatures, but similar carries uncertainty. The measurements have error bars spanning factors of 2 or 3. The DH ratio might be identical to solar system values, or it might differ by 50%. The observations cannot resolve such differences. Larger telescopes, longer integration times, higher spectral resolution might narrow these uncertainties. But the comet will not wait. It approaches perihelion, begins its outward journey, fades as solar distance increases, becomes too faint for detailed spectroscopy. The opportunity for precise compositional analysis spans only months, a narrow window determined by orbital geometry and brightness limitations. Carbon isotopes remain even more uncertain. The ratio of carbon-13 to carbon-12 in carbon monoxide and carbon dioxide could, in principle, reveal formation conditions. C-13 is slightly more massive, slightly more likely to condense at given temperatures, producing isotopic fractionation that depends on where in the disk the ice formed. But measuring this ratio requires resolving spectral lines separated by tiny wavelength shifts, shifts that depend on the isotopic mass difference. Current observations lack sufficient resolution. The carbon in the comet might be isotopically identical to solar system carbon, or it might show enrichments or depletions reflecting different stellar nucleosynthesis in the parent system. The question remains open, unanswered, perhaps unanswerable for this particular comet. What the spectroscopy does not show is as informative as what it does show. No clear signatures of exotic molecules, no compounds unknown in solar system comets, no evidence of chemistry fundamentally different from what occurs in our own protoplanetary environment. This absence suggests either that comet formation is a universal process, governed by physics and chemistry that produce similar outcomes regardless of stellar specifics, or that the sample is biased. Perhaps only comets with compositions similar to ours are easily detected and identified. While exotic compositions go unrecognized or misclassified, the organic molecules remain largely undetectable at the comet's current brightness. Complex carbon-bearing compounds, the tholins and refractory organics that give many comets their reddish coloration that may have delivered prebiotic chemistry to early Earth, require detailed infrared spectroscopy to identify, and the comet's faintness limits spectral quality. Broadband colors suggest the nucleus is dark, reflecting only a few % of incident sunlight, consistent with organic rich surfaces observed on solar system comets. But whether the specific molecules match, whether the comet carries the same amino acid precursors, the same polycyclic aromatic hydrocarbons, the same nitriles and amines, these questions require close-up observation, spacecraft analysis, techniques unavailable for an object passing through so briefly. Only took 4.5 billion years for this ice to travel from formation to observation, and only a few months of observation window to analyze it, a temporal asymmetry that frustrates complete characterization. The comet's composition will remain partially unknown. its full chemical inventory uncatalogued, its isotopic details uncertain. What is known suggests similarity, convergence, chemistry that produces recognizable comets in different stellar systems. What remains unknown spans the details, the subtle differences that might reveal distinct formation pathways, distinct stellar environments, distinct chemical histories. The water that sublimates from the nucleus formed originally as ice crystals in a protoplanetary disk millions of astronomical units across. Vast and cold and dark except for the faint glow of the central protostar. Hydrogen and oxygen atoms, produced in the fusion cores of earlier generation stars, expelled in supernova, mixed into the interstellar medium, drawn together by gravity into a collapsing molecular cloud. These atoms combined in the cold, forming water molecules that then froze onto dust-grained surfaces, accumulating into macroscopic ices through countless collisions. The water remembers none of this. It is simply H2O. Two hydrogen atoms bonded to one oxygen atom at an angle of 104, 5 degrees, behaving according to quantum mechanical principles that do not vary with location or history. And yet, the water traveled. It remained frozen in the comet for billions of years, insulated by layers of dust and more ice, protected from the sparse interstellar radiation field that would slowly sublimate exposed surfaces. The comet's interior maintained temperatures near absolute zero, perhaps 10 or 20 Kelvin, cold enough that molecular motion nearly ceases, that chemical reactions halt, that time itself seems frozen in the stillness of near-total entropy. Only when the comet entered the solar system, approached the sun, began absorbing solar radiation, only then did the temperature rise, the ice warm, the sublimation begin. And only then could spectroscopy reveal composition, could light carry information about molecules formed around another star. The corridor of micrometeoroids carries this composition as well, each particle containing a sample of the comet's ice and dust, a tiny archive of the parent system's chemistry. Most particles are too small to analyze individually, but collectively they form a resource, a distributed sample of extrasolar materials slowly dispersing through the inner solar system. When these particles eventually strike Earth's atmosphere, centuries hence, they will deposit their atoms in the mesosphere, mixing extrasolar oxygen and carbon and nitrogen with terrestrial atmospheric gases. The contribution will be infinitesimal, a few kilograms of material at most, scattered over decades or centuries, diluted to unmeasurable concentrations in Earth's vast atmosphere. But it will occur. This quiet contamination, this exchange of matter between stellar systems, this proof that the galaxy is not partitioned into isolated reservoirs, but connected through the slow traffic of ejected planetesimals, only took spectroscopy to reveal that elsewhere resembles here, at least in chemistry, at least in the compounds that form when hydrogen, carbon, nitrogen, oxygen combine in cold, dark places under the influence of gravity and time. The corridor of dust it leaves behind forms gradually, imperceptibly, particle by particle. Each micrometeoroid separates from the nucleus through processes both violent and gentle, sublimation jets erupting from sun-warmed patches on the surface, carrying dust grains embedded in the ice, radiation pressure accelerating the smallest particles outward once freed from the nucleus, the comet's rotation slowly spinning material away from regions where centrifugal effects exceed local gravity. The nucleus rotates with a period estimated at roughly 8 hours, one full rotation while Earth rotates 3 times. This spin imparting slight outward velocity to dust grains perched on the equatorial regions, launching them into independent orbits when sublimation weakens their attachment. The particles themselves span orders of magnitude in size. The smallest are submicron, fractions of a micrometer across, smaller than bacteria, approaching the wavelength of visible light, composed perhaps of a single mineral grain or a few organic molecules clumped together. These smallest particles experience radiation pressure most strongly. Their surface area to mass ratio is high, meaning solar photons pushing against them impart significant acceleration relative to their tiny mass. They are swept outward, blown away from the sun, forming the dust tail that eventually becomes visible in images as the comet brightens near perihelion. Larger particles, 10 micrometers, 100 micrometers, millimeter scale, experience less relative acceleration from radiation pressure. Their mass increases with the cube of their size, while their cross-sectional area increases only with the square. So larger particles are less affected by light, more governed by gravity and their inherited velocity from the nucleus. These particles drift more slowly away from the comet, forming a denser concentration along the comet's orbital path, a corridor that follows the hyperbolic trajectory more closely than the fine dust blown into the extended tail. The largest fragments, centimeter-scale pebbles, perhaps even meter-scale boulders shed during more violent outbursts or rotational shedding, remain closest to the comet's orbit, their trajectories barely perturbed by non-gravitational forces. These objects are too large to call micrometeoroids. They are small asteroids, fragments of the nucleus itself, rather than dust embedded in ice. Whether such large fragments actually exist in the 3I/Atlas debris stream remains uncertain. No observations have detected them. Their surface area is too small to reflect detectable light at the comet's distance. They might exist as a population of dark, silent boulders trailing the comet. Or they might not. The nucleus might be cohesive enough that large-scale fragmentation has not occurred, that only dust and small grains escape. What is certain is that material is leaving. Photometric observations show the comet's brightness changing over time in ways consistent with continuous mass loss. The coma grows larger, more diffuse. As the comet approaches the sun, this growth indicates increasing sublimation rates, more gas escaping per second, carrying more dust with it. Estimates of the mass loss rate are uncertain. They depend on assumptions about the nucleus size, surface composition, sublimation efficiency, dust-to-gas ratio, but range from tens to hundreds of kilograms per second, over weeks and months. This adds up to millions of kilograms, a measurable fraction of the nucleus's total mass if the nucleus is only a kilometer across. Only took 4 billion years to build the comet through accretion, and a few months of solar heating to begin eroding it, stripping away the outer layers that protect the interior ice. The surface that formed in the cold outer disk of another stellar system now sublimates under the sun's radiation, the boundary between solid and gas advancing inward as material escapes, exposing fresh ice beneath, which then sublimates in turn. The process is self-limiting in one sense as the comet recedes from the sun. Temperatures drop, sublimation slows, the mass loss rate decreases, but irreversible in another. The material lost does not return. It forms the corridor, the trail, the dispersing cloud of particles that will never reassemble into a comet. The corridor itself is not visible to telescopes, not as a distinct structure. Wide-field images of the comet show the coma, the dust tail extending away from the sun, perhaps a faint ion tail of ionized gas following magnetic field lines. But the corridor, the spatial distribution of particles along the orbital path, the region of enhanced dust density trailing behind, this structure is too diffuse, too faint, too extended to photograph. It exists as an inference, a predicted consequence of continuous mass loss over time. Particles shed weeks ago now trail millions of kilometers behind. Particles shed months ago trail tens of millions of kilometers behind. The corridor stretches, lengthens, becomes a thin ribbon of dust following the hyperbolic trajectory, broadening slowly as differential forces, radiation pressure, solar wind, gravitational perturbations disperse the particles laterally. The geometry of this dispersal follows predictable patterns. Particles shed near perihelion, when the comet is closest to the Sun and sublimation is most intense, receive the strongest radiation pressure, are pushed into trajectories that differ most from the comet's own path. Particles shed farther from the Sun. When sublimation is gentler, follow paths closer to the parent trajectory. The result is a corridor with structure, with gradients in particle density and size distribution, with spatial patterns that encode the history of the comet's activity. If the corridor could be mapped in detail, if individual particle orbits could be measured, the map would reveal when and where the comet was most active, which surfaces sublimated most vigorously, how the activity changed as solar heating increased and then decreased. But no such map exists. The particles are too small, too numerous, too dispersed. Observing individual micrometeoroids in interplanetary space requires either passing very close to them with a spacecraft, which detects impacts on dust detectors, or observing them during atmospheric entry, when they heat and ionize and become briefly visible as meteors. Neither method applies to the 3I/Atlas corridor in its current state. No spacecraft travels along the comet's trajectory. The hyperbolic path passes through regions of space where no missions are active, and Earth does not currently intersect the corridor. The geometric alignment is wrong. The orbital planes do not cross at locations Earth will occupy for centuries. What remains mysterious is how long the corridor will persist as a coherent structure. Micrometeoroids in interplanetary space experience numerous perturbations that gradually disperse their orbits. Radiation pressure varies with particle size and continues acting on particles throughout their journey, slowly changing their trajectories in ways that depend on solar distance and particle optical properties. The Poynting-Robertson effect, drag caused by the aberration of sunlight as particles orbit the Sun, causes particles to spiral gradually inward, though this effect becomes negligible once the comet and its debris stream have receded beyond a few astronomical units. Gravitational perturbations from planets, especially Jupiter, will eventually scatter the particle orbits, broadening the corridor until it merges with the background zodiacal cloud. Timescales for dispersal are difficult to calculate precisely. Small particles might disperse within centuries, their orbits randomized by radiation pressure and perturbations. Larger particles might maintain coherent orbits for millennia, their trajectories stable enough that the corridor remains a distinct structure, a recognizable stream of enhanced particle density for thousands of years after the comet's departure. But eventually, within tens of thousands of years certainly, perhaps much sooner, the corridor will fade, the particles spreading throughout the inner solar system, becoming indistinguishable from the general population of interplanetary dust. The particles themselves, however, do not fade. They persist as physical objects, silicate grains and organic matter, and perhaps fragments of water ice if sufficiently shielded. Each particle carries its composition indefinitely, traveling through space until some event terminates its journey: atmospheric entry and ablation, collision with a larger body, gradual erosion by interstellar gas if it escapes the solar system entirely, solar heating and sublimation if it contains remaining volatiles and drifts too close to the Sun. Most will likely drift outward, following their inherited hyperbolic trajectories, eventually rejoining the interstellar medium they came from, carrying their atoms back into the space between stars. Only took the comet's passage to create this corridor, this temporary enhancement in micrometeoroid density along a specific trajectory, and only time, patient, unrelenting time, to dissolve it, to scatter the particles, to erase the geometric structure that briefly encoded the comet's path through the inner solar system. The corridor is ephemeral in astronomical terms, lasting perhaps 10,000 years if the particles disperse slowly, a tiny fraction of the comet's age, a barely measurable interval in galactic history. But while it exists, a thin ribbon of extrasolar dust threading through space, invisible and silent. a trail leading nowhere except outward, away, back toward the dark. How radiation pressure sculpts the tail begins with photons, massless packets of electromagnetic energy, streaming outward from the sun at the speed of light, 300,000 kilometers per second, 8 minutes from surface to Earth, hours to the comet's current position beyond the inner planets. Each photon carries momentum, despite carrying no mass, a consequence of relativistic mechanics where energy and momentum relate through equations that remain valid even when rest mass equals zero. When photons strike matter, when they reflect off a dust grain's surface or are absorbed into its structure, they transfer this momentum, exerting a tiny push, an acceleration that depends on the photon's energy and the particle's mass and cross-sectional area. For large objects like planets or the comet's nucleus, radiation pressure is negligible. The sun pushes on Earth with a force of several million newtons, which sounds substantial until compared to Earth's mass. The resulting acceleration is unmeasurable, dwarfed by gravitational and tidal forces. But for micrometeoroids, particularly submicron particles with high surface area to mass ratios, radiation pressure becomes significant. A particle 1 micrometer across experiences acceleration from sunlight that can rival or exceed solar gravitational acceleration at distances of a few astronomical units. These smallest particles are effectively blown outward, swept away from the sun by the continuous wind of photons, accelerating as they travel until they reach terminal velocity, determined by the balance between radiation pressure and diminishing solar intensity with distance. The result is two tails, a structure common to active comets observed throughout history, noted by Chinese astronomers 2 millennia ago, sketched by European observers during the Renaissance, photographed in detail since the advent of astrophotography. The dust tail forms from particles large enough to remain somewhat governed by gravity, but small enough to experience substantial radiation pressure. These particles, typically 1 to 10 micrometers, are pushed outward and backward, creating a curved tail that follows neither the comet's orbital path nor a straight line away from the sun, but a compromise between these directions. A graceful arc determined by the balance between inherited orbital velocity and radiation acceleration. The ion tail, by contrast, forms from ionized gas molecules, atoms that have lost electrons to solar ultraviolet radiation, becoming charged particles that respond to magnetic forces rather than radiation pressure alone. The solar wind, the continuous outflow of charged particles from the sun's corona, carries magnetic field lines outward, and these field lines drag ionized molecules with them, pulling the ion tail into a long, straight structure pointing directly away from the sun regardless of the comet's direction of motion. The ion tail can extend for millions of kilometers, sometimes tens of millions, a pale blue structure visible in photographs, colored by emission from ionized carbon monoxide that fluoresces in sunlight. For 3I/Atlas, both tails are present but subtle. The comet is not particularly active compared to famous comets like Hale-Bopp or Hyakutake, comets that develop tails visible to the naked eye, stretching across degrees of sky. Atlas remains faint, its tails detectable in telescopic images, but modest in extent. Perhaps a few arc-minutes long as seen from Earth, corresponding to actual lengths of hundreds of thousands of kilometers, vast by human standards, modest by cometry standards. The dust tail shows a gentle curve, particles of different sizes creating slight stratification, smaller particles pushed farther from the Sun-Comet line, larger particles following trajectories closer to the comet's orbital path. What remains mysterious is the exact composition of the dust forming the tail, the mineralogy of the particles. Are they primarily silicates, olivine, pyroxene, the minerals that constitute rocky planets and asteroids? Or do they contain substantial organic components, complex carbon-bearing molecules? The refractory tholins that give comets their dark surfaces, Spectroscopy of the dust tail might reveal this composition through analysis of reflected sunlight, looking for absorption features characteristic of specific minerals or molecular bonds. But the tail's faintness limits spectral quality. Observations capture only broadband colors, insufficient to identify specific compounds. The size distribution of tail particles can be inferred indirectly through photometric analysis, measuring how the tail's brightness varies with distance from the nucleus and with angle from the Sun-Comet line. Smaller particles scatter light differently than larger particles, produce different brightness gradients, create different degrees of curvature in the tail's shape. Models that fit these observations suggest a size distribution ranging from submicron to perhaps 100 micrometers, with most mass concentrated in particles around 10 micrometers, roughly the size of human red blood cells, small enough to remain suspended in Earth's atmosphere if they were to drift there, large enough to survive atmospheric entry and reach the ground as micrometeorites, though modified by heating during descent, only took the sun's radiation to separate particles by size, to sort them through radiation pressure into a tail stratified by mass and surface properties, and to stretch this sorted sample across hundreds of thousands of kilometers where it becomes visible, briefly, before dispersing into the general interplanetary dust population. The tail is temporary, existing only while the comet remains close enough to the sun that sublimation continues, that gas flows outward carrying dust, that solar radiation is intense enough to push particles into visible structures. As the comet recedes, as it climbs back up the gravitational well toward interstellar space, sublimation will slow. Gas production will decrease. The tail will fade and disappear, leaving only the dispersed corridor of particles that no longer forms a visible structure. The ion tail behaves differently, governed by electromagnetic forces rather than radiation pressure alone. The solar wind, a plasma of electrons and protons streaming outward from the sun at 400 kilometers per second, carries the sun's magnetic field with it, frozen into the plasma through the high conductivity of ionized gas. This interplanetary magnetic field is not uniform. It forms a spiral pattern, the Parker spiral, shaped by the sun's rotation combined with the wind's radial outflow. Magnetic field lines thus curve, creating sectors of different polarity that sweep past planets and comets as the sun rotates. When the comet's ionized gas, the coma's outer regions where ultraviolet radiation has stripped electrons from carbon monoxide and water molecules, encounters these magnetic field lines, electromagnetic forces act. Charged particles gyrate around field lines, effectively trapped, and as the solar wind flows outward, it drags the field lines and their attached ions with it. The ion tail thus streams directly away from the sun, aligned with the local magnetic field direction, sometimes showing fine structure, rays or streamers, where different field lines carry ions at slightly different velocities, or where magnetic reconnection events suddenly release packets of plasma that propagate down the tail as discrete clouds. For 3I/Atlas, the ion tail appears straight in images, a faint bluish streak extending anti-sunward, flickering slightly in brightness as solar wind conditions vary, as the density and velocity of the plasma flowing past the comet changes with solar activity. The tail's blue color comes from carbon monoxide ions, CO+ molecules that fluoresce in sunlight, absorbing ultraviolet photons and re-emitting visible light at wavelengths around 400 nanometers. In the blue part of the spectrum, this emission provides another way to measure the comet's gas production rate. The brightness of the ion tail is proportional to the number of CO+ ions present, which in turn depends on how much carbon monoxide is sublimating from the nucleus. What remains uncertain is how the ion tail will behave as the comet passes through different regions of the heliosphere, through sectors of the interplanetary magnetic field with different properties, through regions affected by coronal mass ejections or high-speed solar wind streams. The ion tail is dynamic, responsive to space weather in ways the dust tail is not. If a strong interplanetary shock, a fast-moving disturbance in the solar wind triggered by a coronal mass ejection, were to overtake the comet, the ion tail might disconnect entirely. A dramatic event where magnetic reconnection severs the tail from the coma, causing the old tail to drift away while a new tail forms behind it. Such disconnection events have been observed in other comets, documented photographically, analyzed as natural experiments revealing the complex interaction between comets and the solar wind. But 3I/Atlas may pass through the inner solar system without such drama. The Sun's activity level during the comet's passage is moderate, neither particularly active nor particularly quiet, producing steady solar wind without major eruptions. The ion tail may simply persist, streaming steadily away from the Sun, gradually fading as the comet recedes and the gas production decreases, disappearing smoothly rather than dramatically, becoming too faint to detect as the comet returns to interstellar cold. Only took physics, electromagnetism, radiation pressure, gravity, to create these two distinct tails from the same source, to separate charged particles from neutral dust, to sculpt visible structures from invisible gas and micrometeoroids, and to make the comet's passage temporarily obvious, briefly beautiful. Photographable for the few months it spends within a few astronomical units of the Sun before fading back into darkness, trailing two tails that themselves fade, dissolving into the background populations of ions and dust that fill the space between planets. The silence of the coma begins with vacuum, space so empty that molecules travel centimeters or meters between collisions. Compared to nanometers in Earth's atmosphere, where air molecules jostle constantly, the coma is not truly empty. It contains gas sublimated from the nucleus, typically water vapor with admixtures of carbon monoxide, carbon dioxide, other volatiles, all expanding outward at velocities around 1 kilometer per second, typical speeds for gas escaping from a comet's weak gravity. But the density is low, perhaps 1 billion molecules per cubic centimeter near the nucleus, decreasing inversely with the square of distance, falling to 1 million per cubic centimeter at the coma's outer edge. Thousands of kilometers from the nucleus. 1 billion molecules per cubic centimeter sounds dense until compared to Earth's atmosphere at sea level, which contains roughly 25 million trillion molecules per cubic centimeter, 25 billion times denser than the inner coma. At such low densities, the coma cannot support sound waves. Sound requires compression waves, requires molecules to collide frequently enough to transmit pressure variations, to create regions of higher and lower density that propagate through the medium. In the coma, molecules are too sparse, collisions too infrequent. A sound wave attempting to propagate would dissipate immediately, its energy lost to the expansion of the gas, unable to maintain coherence over distances larger than the mean free path between collisions. So the coma is silent, not quiet. Quietness implies low amplitude sound, whispers, distant murmurs. Silent means absence, means sound cannot exist, means the physical prerequisites for acoustic waves are missing. An observer floating in the coma would hear nothing, not even their own breathing. Though in reality, an observer would need a spacesuit and would hear the mechanical sounds of life support systems conducted through solid materials, through helmet and body contact, but would hear nothing from the surrounding gas. No wind despite the gas flowing past at kilometer per second velocities. No hiss or roar or whistle. The coma glows, though faintly. Through fluorescence and scattering, water molecules absorb solar ultraviolet photons, become excited to higher energy states, decay back to lower states by emitting visible and infrared photons. This fluorescence produces faint emission lines, particularly in the red part of the spectrum where hydroxyl radicals, OH fragments from dissociated water molecules, emit strongly, The glow is too faint for human eyes to detect without long exposures. The coma appears dark to hypothetical observers unless they wait minutes or hours for their cameras to integrate enough photons to form visible images. But the glow exists. Measurable. Quantifiable. Providing one method to estimate gas production rates and coma composition. Dust particles in the coma scatter sunlight, reflecting and refracting incident photons, contributing additional brightness that combines with the gas fluorescence to create the visible coma seen in telescope images. The scattered light is sunlight, essentially the sun's spectrum reflected, though modified slightly by the wavelength-dependent scattering efficiency of dust grains, their composition and size distribution determining how much blue light versus red light is scattered. The dust makes the coma appear more yellow or reddish than the blue-white ion tail, a color difference visible in good photographs. A subtle cue revealing the different physical processes at work. What remains mysterious is the temperature within the coma, how thermal energy distributes among the gas molecules and dust particles. Gas expanding rapidly cools adiabatically. The expansion does work against the surrounding pressure, negligible as it is. And more importantly, the fastest molecules escape preferentially, carrying away kinetic energy and leaving slower, cooler molecules behind. Measurements and models suggest temperatures in the inner coma near the nucleus might reach 200 to 300 Kelvin, below water's freezing point but above absolute zero. But these temperatures are kinetic temperatures, describing the average speed of molecules, not equilibrium temperatures in the thermodynamic sense. The concept of temperature becomes ambiguous in such rarefied environments. Temperature in dense gases relates to the thermal equilibrium established through frequent collisions, with energy distributing according to Maxwell-Boltzmann statistics. In the coma, collisions are rare enough that different particle populations, water molecules, carbon monoxide molecules, dust grains of different sizes might have different kinetic energy distributions, different temperatures, if temperature is defined by average kinetic energy. The gas and dust are not in thermal equilibrium with each other or with the surrounding sunlight. They are in a transitional state, expanding, cooling, fragmenting, ionizing, gradually losing coherence as a thermodynamic system. Only took sublimation to create this expanding cloud, and only solar radiation to make it visible, and only vacuum to make it silent, a vast region of space, larger than many planets, filled with gas and dust in quantities that would be considered excellent vacuum in any laboratory, yet representing substantial mass loss for the comet, millions of kilograms of material escaping into space, dispersing, joining the interplanetary medium. The coma is not a stable structure. It exists only as long as sublimation continues. As long as the nucleus remains warm enough to release gas, when the comet recedes, when solar heating diminishes, the coma will fade. The gas production will slow and stop. The coma will collapse back toward the nucleus or dissipate entirely into space, leaving only the dark nucleus traveling through darkness. The ice sublimating to form the coma undergoes phase transition directly from solid to gas, bypassing the liquid phase that requires higher pressures than exist on the nucleus surface. This sublimation is endothermic, requires energy input provided by absorbed sunlight, and occurs most rapidly on surfaces facing the sun, creating asymmetric gas production. Jets preferentially directed sunward and then swept back by the gas's expansion and by radiation pressure on entrained dust. These jets create structure in the inner coma, regions of enhanced density streaming away from active areas on the nucleus, sometimes visible in high-resolution images as rays or fans extending outward before merging into the more uniform outer coma. The nucleus itself rotates, typically with periods of hours to days, causing the active regions to rotate in and out of sunlight, creating time-variable gas production, pulsed jets that appear and disappear with the rotation period. For 3 Ice/Atlas, The rotation period is estimated at roughly 8 hours. Though uncertainty spans several hours, the nucleus is too small and distant to resolve directly. So rotation period must be inferred from periodic variations in brightness or gas production, and these variations are subtle, sometimes ambiguous. The 8-hour period means jets reorient 3 times per Earth day, gas production varying sinusoidally as active regions rotate through noon and midnight on the nucleus, creating complex patterns in the inner coma that evolve over hours. Frozen in individual telescope images, but dynamic when images are sequenced into movies. What the coma does not contain is liquid. No droplets of water, no pools or lakes or any condensed phase. The pressure is far too low. Water's triple point requires pressures above 600 pascals, and the coma's pressure is perhaps a billionth of a pascal, a trillionth of Earth's atmospheric pressure. Water exists only as ice in the nucleus and vapor in the coma, with no intermediate liquid phase. This is true throughout most of the solar system. Liquid water exists stably only on Earth's surface and perhaps in subsurface oceans of icy moons where pressure is maintained by overlying ice shells. The comet's water, formed as ice in the parent protoplanetary disk billions of years ago, will never experience liquidity. It transitions directly from solid to gas, from ordered crystalline structure to free-flying molecules, maintaining this vapor phase until molecules either recondense onto interplanetary dust grains far from the Sun or dissociate into hydrogen and oxygen under continued ultraviolet irradiation. Only took proximity to the Sun to transform ice into this silent, glowing cloud, and only distance will reverse the transformation, will shut down sublimation, will leave the nucleus dark and inactive, its remaining ice preserved indefinitely in the cold of interstellar space, frozen at temperatures approaching absolute zero. Molecular motion nearly ceased, entropy nearly minimized, time slowed to the pace of radioactive decay and rare cosmic ray interactions, the only processes still occurring in matter so cold and isolated. The coma extends outward to boundaries that are not sharp, not defined by any sudden transition. Instead, the gas density simply decreases, falling off smoothly with distance from the nucleus, eventually becoming indistinguishable from the background interplanetary medium, the sparse solar wind plasma, the trace hydrogen atoms that fill space between planets, the cosmic rays and solar energetic particles that constitute the ambient radiation environment. Where the coma ends depends on what threshold is chosen for detection, what minimum density is considered significant. Astronomers sometimes define the coma as extending to where gas density equals background density, but this boundary shifts constantly as gas production varies, as solar wind conditions change, as the definition of background is refined. In practice, the visible coma, the region bright enough to photograph, extends perhaps 100,000 kilometers from the nucleus, roughly a quarter of the Earth-Moon distance. Though the exact size depends on the comet's activity level and the sensitivity of observations, the actual gas distribution extends farther, detectable through specialized instruments that can measure faint emission lines or scattered sunlight at levels invisible to conventional imaging. The hydrogen cloud, formed when water molecules dissociate under ultraviolet light, releasing hydrogen atoms that then glow through Lyman alpha emission, extends millions of kilometers, sometimes tens of millions, creating a vast envelope around the comet that can be observed only with ultraviolet telescopes above Earth's atmosphere, which absorbs Lyman alpha photons before they reach ground-based instruments. This hydrogen cloud is also silent, also too rarefied to support sound, but even more diffuse than the main coma, with densities perhaps 1,000 atoms per cubic centimeter, comparable to the best laboratory vacuums achieved on Earth. The hydrogen atoms travel outward at speeds around 20 kilometers per second, much faster than the heavier water molecules, accelerated by radiation pressure that affects light hydrogen atoms more efficiently than molecules. These atoms will escape the solar system entirely, carrying their mass and kinetic energy into interstellar space, becoming part of the general population of neutral hydrogen that fills the galaxy. The raw material for future star formation in molecular clouds billions of years hence. Only took sunlight to dissociate water molecules, to free hydrogen atoms, to accelerate them outward, and silence accompanies the entire process. The photodissociation makes no sound. The hydrogen's escape makes no sound. The gradual dispersal of atoms across cubic astronomical units of space occurs in perfect acoustic stillness. If the coma could be heard, if sound could propagate through such vacuum, perhaps it would roar with the violence of sublimation, with the expansion of gas, with the dissociation of molecules under ultraviolet bombardment. But sound cannot propagate, and the coma remains silent. A vast cloud of glowing gas and dust expanding outward at supersonic velocities, supersonic meaning faster than sound would travel if sound could travel, all occurring in silence because the medium cannot support the compression waves that would constitute sound. The paradox of supersonic expansion in silence is not really paradoxical. It simply reflects the different physical requirements for bulk fluid motion versus acoustic waves. Gas can flow, can have velocity, can expand, can even develop shock waves where expansion speed exceeds the local speed of sound, though local speed of sound becomes undefined when collision rates are too low for sound waves to exist. The gas molecules in the coma are moving, carrying momentum and kinetic energy, but they are not communicating with each other acoustically. Each molecule travels ballistically, following its individual trajectory determined by its velocity at the moment it sublimated or was last scattered by a collision. The molecules form a statistical ensemble, a gas in the kinetic theory sense, but not an acoustic medium. Not a substance capable of transmitting organized pressure variations. An observer with perfect hearing, floating in the coma, would experience this profound silence, would sense the gas molecules striking their spacesuit at kilometer-per-second speeds, billions of impacts per second on each square centimeter of surface, but would hear nothing, because hearing requires pressure waves in air conducting through ear canals to tympanic membranes, requires pressure variations at frequencies between 20 and 20,000 Hz, requires an atmosphere dense enough to transmit these variations. The coma offers none of this. It offers only ballistic molecules, each following its own path, collectively producing a pressure, a force per unit area, but not producing organized waves, not creating the temporal and spatial patterns that constitute sound. What the observer might hear, hypothetically, is their own body sounds conducted through bones and tissues, heartbeat, breathing, blood flow, and the mechanical sounds of life support equipment conducted through solid materials. But from the coma itself, nothing. Not wind despite the gas flowing past, not hissing despite the sublimation ongoing nearby, not impacts despite millions of dust particles larger than the observer drifting through the same volume of space. The dust particles are too small to produce audible impacts even if there were air to conduct the sound of impacts. A grain 1 micrometer across, traveling at 1 kilometer per second, carries kinetic energy measured in picojoules, releasing this energy on impact but producing no sound waves, only local heating and perhaps fragmentation, effects that remain silent at such scales. Only took the absence of atmosphere to create this silence. And the presence of gas, paradoxically, does not alleviate it. Because the gas is too thin, too dispersed, too transitional between solid and vacuum to support the collective oscillations that sound requires. The coma thus demonstrates that emptiness admits degrees, that vacuum is not binary, but gradual, that between the dense atmospheres of planets and the near-perfect vacuum of intergalactic space lies this intermediate state, enough molecules to sublimate and glow and form structures visible across millions of kilometers, but not enough molecules to conduct sound, to support weather, to create the acoustic environment that terrestrial life associates with the presence of gas. The silence will persist as long as the coma persists, as long as sublimation continues, as long as gas expands outward through space, too empty to make sound from its motion. And when the coma fades, when the comet recedes and sublimation stops, the silence will deepen further, becoming the perfect silence of hard vacuum, of space containing only the rare solar wind particles and cosmic rays, of emptiness approaching the mathematical ideal of nothing, where not only sound, but even the preconditions for sound have vanished, leaving only electromagnetic waves, light, radio, infrared, as the sole means of transmitting information through the void. Comparing 3 I/Atlas to 1 I/Oumuamua and 2 I/Borisov begins with acknowledging how different these 3 interstellar visitors appear. Despite sharing the fundamental property of hyperbolic trajectories, of positive orbital energy, of origin beyond the Sun's gravitational family, the first, Oumuamua, Hawaiian for scout or messenger from afar arriving first, passed through the inner solar system in October 2017, discovered by the Pan-STARRS telescope in Hawaii weeks after its closest approach to the Sun. What made Oumuamua remarkable was not its interstellar origin, which took days of orbital calculations to confirm, but its appearance: no coma, no tail, no visible cometary activity, despite passing well within Earth's orbit where solar heating should trigger sublimation in any icy body. Oumuamua appeared asteroidal, a dark, elongated object tumbling through space with a rotation period of roughly 8 hours, its brightness varying by a factor of 10 as different aspects rotated into view, suggesting an elongated shape, perhaps 10 times longer than wide, cigar-shaped or perhaps pancake-shaped. The photometric observations unable to distinguish between these geometries. Its spectrum showed no clear signatures of ice or gas, only reddish coloration consistent with organic rich surfaces similar to outer solar system objects. For weeks, Oumuamua was classified as an interstellar asteroid, the first confirmed rocky body from another stellar system, evidence that other stars produce not only comets but also rocky planetesimals. Then the trajectory analysis revealed anomalies. Oumuamua was accelerating slightly as it left the solar system, accelerating in a direction away from the Sun beyond what solar gravity alone could explain. The acceleration was small, measured in millimeters per second, barely detectable in the astrometric data, but statistically significant, requiring explanation. The most plausible explanation was outgassing, even without visible coma or tail. Oumuamua might be releasing small amounts of gas that acted like rocket thrust, pushing it slightly off its gravitational trajectory. This outgassing would require the object to contain volatiles, to be at least partially icy, to be comet-like despite appearing asteroidal. What remains mysterious about Oumuamua is why the outgassing produced no visible coma, why no gas or dust was detected despite multiple observations with sensitive instruments. Possible explanations include unusual composition, perhaps nitrogen ice or carbon monoxide ice rather than water ice, volatiles that sublime without producing visible comas, or unusual structure. Perhaps a thick crust of refractory material covering ices beneath, insulating them except for small vents that released gas without entraining enough dust to create observable tails. Or perhaps the acceleration had a different cause, radiation pressure acting on an unusually low-density object, or even more exotic possibilities involving hydrogen icebergs or light sails. Proposals that strained credulity but could not be definitively ruled out given the limited observations. Only took Oumuamua 11 days to pass through the region where detailed observations were possible, and by the time its interstellar nature was confirmed, the object was already fading, receding, becoming too faint for spectroscopy or high-resolution imaging. The opportunity for complete characterization was missed, lost to discovery lag and the object's high velocity. What remains are grainy images showing an elongated point source, a spectrum with low signal-to-noise showing general reddish color, astrometric measurements revealing the anomalous acceleration, and a catalogue of unanswered questions about composition, structure, origin, and the mechanism behind the non-gravitational force affecting its trajectory. The second interstellar object, 2I/Borisov, discovered in August 2019 by amateur astronomer Gennady Borisov using a telescope he built himself, offered a stark contrast to Oumuamua. Borisov appeared unambiguously cometary from the first observations. Obvious coma, clear tail, spectroscopic signatures of gas emission, behavior entirely consistent with comets native to the solar system. Its composition, as revealed through spectroscopy, included water vapor, carbon monoxide, carbon dioxide, cyanide compounds, a chemical inventory closely matching solar system comets, particularly those believed to have formed in the outer regions of the protoplanetary disk. Borisov's trajectory was also clearly hyperbolic, with eccentricity around 3, 4, even more extreme than Atlas, indicating higher velocity relative to the Sun, perhaps suggesting ejection from a more energetic encounter or formation in a system with different characteristics. The comet brightened as it approached perihelion, developed a substantial tail, fragmented into at least 2 pieces during its passage, behavior entirely normal for comets experiencing thermal stress from solar heating, internal structures failing under thermal expansion, volatile-rich regions sublimating preferentially and creating stresses that crack the nucleus. What made Borisov scientifically valuable was the advance warning. Unlike Oumuamua, discovered after perihelion when already departing, Borisov was discovered months before its closest approach, allowing telescopes worldwide to observe it throughout its passage, to track changes in brightness and gas production, to obtain detailed spectra at multiple wavelengths, to coordinate observations across many facilities. The Hubble Space Telescope observed Borisov repeatedly, resolving the nucleus and coma, measuring the nucleus size at roughly 400 meters, smaller than many solar system comets, but large enough to maintain structural integrity despite thermal stress. Ground-based telescopes measured gas production rates, dust-to-gas ratios, rotation period, sublimation patterns. The result was the most complete characterization of an interstellar object achieved to date, revealing that at least some interstellar comets closely resemble solar system comets in composition, behavior, and structure. Borisov suggested that comet formation is a universal process, producing similar outcomes in different stellar systems, perhaps because the physics and chemistry of cold protoplanetary disks operate similarly regardless of the parent star's specifics, at least for solar-type stars with similar metallicities and disk conditions. Only took 2 interstellar comets, Borisov and now Atlas, to establish this pattern. Though pattern recognition from 2 examples remains tentative, requiring confirmation from additional objects. Now 3I/Atlas offers a third data point, intermediate between Oumuamua's enigmatic inactivity and Borisov's clear cometary behavior. Atlas shows definite cometary activity, coma, and tails visible in observations, but remains fainter than Borisov, less active, suggesting either a smaller nucleus, lower volatile content, or less efficient sublimation, perhaps due to composition or surface properties. Spectroscopic observations of Tailless, though less detailed than those of Borisov due to the comet's fainter magnitude, show water vapor and carbon monoxide, confirming cometary composition similar to both Borisov and solar system comets. The trajectory of Atlas, eccentricity around 1.4, excess velocity around 26 kilometers per second, falls between Oumuamua's moderate eccentricity of about 1.2 and Borisov's high eccentricity of 3.4. This intermediate value suggests an ejection less energetic than whatever expelled Borisov, but more energetic than Oumuamua's departure from its parent system. The range of velocities among these three objects hints at the diversity of ejection mechanisms, the various dynamical pathways through which comets escape their birth systems, gentle perturbations that barely achieve escape velocity, violent encounters that impart high excess speeds, intermediate cases where multiple smaller perturbations accumulate over time to gradually increase orbital energy until it becomes positive. What remains uncertain is how representative these three objects are of the broader population of interstellar visitors. Detection bias strongly affects the sample. Large, active comets are easier to discover than small, inactive ones. Objects passing close to Earth are more readily detected than those traversing the outer solar system. Arrivals during periods of intensive sky surveys are more likely to be found than arrivals when observational coverage is sparse. Statistical models attempting to correct for these biases suggest that Oumuamua-like inactive objects might be more common than Borisov-like active comets. Though uncertainties span orders of magnitude, the three objects also reveal different stellar systems, three different formation environments separated by light years of space and possibly billions of years of time. Oumuamua's trajectory traced back toward the direction of Vega, though Vega's position millions of years ago when Oumuamua might have been ejected was different, making definitive origin identification impossible. Borisov's trajectory points back toward a region of the sky containing no obvious candidate parent stars within reasonable travel times. Atlas originates roughly from Ursa Major, but, as with the others, the exact parent system remains unidentified, lost in the scatter of hundreds of possible sources and the uncertainties of reconstructing million-year trajectories through a dynamically evolving stellar neighborhood. Only took 3 confirmed interstellar objects to reveal that elsewhere produces variety, that different systems eject different types of bodies, that the diversity of solar system, small bodies, from icy comets to rocky asteroids to mixed compositions, is mirrored in interstellar space, in the population of ejected planetesimals drifting between stars. And only 3 objects to demonstrate how little is known, how much remains mysterious. How many questions each detection raises rather than answers? Are interstellar comets typically active or inactive? What range of compositions exists among objects from different systems? How do ejection mechanisms vary with stellar and planetary properties? How many interstellar objects pass through undetected for everyone discovered? The corridors these objects leave, the trails of gas and dust marking their passages, are themselves diverse. Oumuamua left essentially no corridor, no detectable debris trail, consistent with its apparent lack of activity. Borisov left a substantial trail, particles shed over months of active sublimation, dispersing along its hyperbolic trajectory in a stream that will gradually spread and fade but might remain detectable for centuries as a distinct enhancement in micrometeoroid density. Atlas is leaving its own corridor, intermediate in density and extent, a ribbon of particles trailing outward behind the comet, encoded with information about the parent system's composition, about the comet's formation and evolution, about the processes that expelled it billions of years ago and brought it here, to this particular trajectory intersecting Earth's vicinity at this particular moment in galactic history. Only took 3 visitors to hint at the population beyond, at the vast number of ejected comets drifting through the galaxy, each carrying samples of its parent system, each a potential source of information about planet formation around other stars, each following its own lonely trajectory through the dark, most never approaching any star closely enough for solar heating to create comas and tails, most remaining frozen and invisible. Dark ice moving through darkness, silent couriers between stellar systems in a galaxy where such exchanges occur continuously but rarely coincide with observation. The nucleus that never fully brightened remains faint throughout its passage through the inner solar system. Dimmer than predictions, dimmer than similar-sized comets should appear at comparable distances from the Sun. This underbrightness is not dramatic, The comet does brighten as it approaches perihelion, does develop the expected coma and tails, does show clear cometary activity. But the magnitude measured by photometric observations consistently falls below the values predicted by models that assume standard cometary behavior, standard sublimation rates, standard dust production. The discrepancy amounts to perhaps 1 to 2 magnitudes, which translates to factors of 3 to 6 in brightness, enough to be statistically significant, enough to require explanation. The simplest explanation is that the nucleus is smaller than initial estimates suggested. Nucleus size is difficult to determine directly for faint, distant comets. The nucleus itself is rarely resolved, appearing as a point source surrounded by the diffuse coma. Size estimates instead derive from brightness measurements combined with assumptions about surface reflectivity, how much incident sunlight the nucleus reflects versus absorbs. If the nucleus is darker than assumed, reflecting only 1 or 2% of sunlight instead of 4 or 5%, the same brightness corresponds to a smaller nucleus. A nucleus, half the diameter, contains 1/8 the mass, produces proportionally less gas and dust when it sublimates, and thus creates a fainter coma and tail. Alternatively, the nucleus might be depleted in volatiles, its surface composition dominated by refractory materials, silicates, organic compounds, minerals that do not sublime readily, with ice buried beneath insulating layers. Such a structure is common in evolved comets, objects that have made many passes through the inner solar system, gradually losing their surface ices and building up non-volatile crusts that inhibit further sublimation. But 3I/Atlas is making its first and only passage through this solar system. It has never experienced solar heating before, has no history of previous perihelion passages to deplete its volatiles. If its volatiles are already depleted, the depletion must have occurred either in its parent system, perhaps through multiple perihelia around its birth star, or during its long interstellar journey through mechanisms less obvious than solar heating. Cosmic ray bombardment offers one such mechanism. Galactic cosmic rays, high-energy protons and atomic nuclei streaming through the galaxy, accelerated to near-light speeds by supernova shocks and other violent processes, continuously irradiate interstellar comets. These particles penetrate the surface, depositing energy, breaking chemical bonds, driving radiolysis reactions that alter molecular structures. Over millions of years, cosmic ray exposure can process surface ices, converting simple molecules like water and carbon monoxide into more complex refractory organics, darkening the surface, reducing sublimation efficiency. The dose accumulated depends on exposure time and shielding. Surfaces are affected more than interiors, potentially creating a processed crust millimeters or centimeters thick while preserving pristine ice beneath. What remains mysterious is whether cosmic ray processing alone can account for the observed dimness, or whether additional factors contribute. Thermal processing during the comet's formation or during passages near its parent star might have depleted surface volatiles before ejection. Collisions with other planetesimals during the early chaotic phase of its parent system's development might have fractured the nucleus, exposing fresh ice that then sublimated during subsequent perihelia, leaving a volatile depleted remnant. Or the dimness might reflect compositional differences unrelated to depletion. Perhaps the comet formed in a region of its parent disk where water ice was less abundant, where carbon dioxide or carbon monoxide dominated. Volatiles that sublime at different rates and produce different brightness characteristics. Only took billions of years and light years of travel to deliver this comet here, and only a few months of observations to reveal that it defies simple predictions, that standard models do not capture its behavior, that interstellar comets introduce variables not present in solar system objects, variables related to formation in unknown stellar environments, processing during unobserved journeys, histories that can only be inferred from current observations that themselves carry uncertainties and ambiguities. The dimness is a puzzle piece, a data point, an anomaly that may or may not prove significant once additional interstellar comets are discovered and characterized. Once the sample size grows large enough to distinguish individual variations from systematic differences between interstellar and native populations. The perihelion distance, the comet's closest approach to the Sun, is approximately 0.7 astronomical units, inside Earth's orbit, well within the distance where solar heating should trigger vigorous sublimation in any body containing substantial water ice. At this distance, solar flux is twice Earth's solar constant, intense enough to raise surface temperatures to around 200 Kelvin on directly illuminated areas, well above water ice's sublimation point in vacuum. Gas should stream from the nucleus at rates of hundreds of kilograms per second. The coma should brighten dramatically. The dust tail should become obvious even to small telescopes. Yet Atlas remains modest. Its gas production rates estimated from spectroscopy at perhaps 1/10 to 1/4 the values expected for its estimated nucleus size. The rotation of the nucleus might contribute to the dimness if active regions, areas where ice remains accessible at the surface, cover only a small fraction of the total surface area. If most of the nucleus is coated in non-volatile crust, with only isolated vents or fractures allowing gas to escape, the total sublimation rate will be correspondingly reduced. Observations hint at asymmetric gas production, with jets preferentially emanating from specific regions that rotate in and out of sunlight, creating time-variable brightness and spectroscopic signatures. But the details remain unclear. The nucleus is too small and distant to resolve surface features, too faint for detailed rotational mapping of active areas. What is certain is that the comet will not brighten further. Perihelion has passed. Solar distance now increases with each hour as the comet climbs back up the gravitational well toward interstellar space. The brightness peaked weeks ago, perhaps reaching magnitude 16 or 17, still far below naked eye visibility. Requiring moderate-sized telescopes and dark skies for detection, accessible to amateur astronomers with proper equipment and knowledge, but invisible to casual observers. Now the comet fades, gradually but inexorably, magnitude increasing, numbers getting larger, brightness getting dimmer, a counterintuitive convention in astronomy, as the inverse square law dictates the relationship between solar distance and reflected sunlight. Only took one perihelion passage to reveal the comet's properties, and only one perihelion passage will ever occur. Unlike solar system comets that return century after century, allowing observers across generations to refine measurements and test predictions, interstellar visitors offer single opportunities. The observations obtained during Atlas's passage are the only observations that will ever be obtained. The comet will recede beyond the range of even the largest telescopes within a year, will exit the solar system entirely within a few years, will never return. What remains unknown will remain unknown, unless future missions can intercept interstellar comets during their passages, deploying spacecraft to match trajectories and perform close-up observations impossible from Earth's distance. Such missions have been proposed but not yet developed. The challenge is timing and trajectory. Interstellar objects arrive with little warning, their hyperbolic paths giving only months from discovery to departure, insufficient time to design, build, and launch interceptor spacecraft using current technology. Pre-positioned spacecraft waiting in dormant modes for interstellar arrivals could respond faster, but the cost of maintaining such sentinels and the low frequency of detectable interstellar visitors make this approach impractical with present budgets and priorities. Future developments, faster propulsion systems, automated spacecraft manufacturing, increased sky survey coverage providing earlier warnings might eventually enable interstellar object missions. But for now, Earth-based telescopes provide the only means of study, and their limitations guarantee that many questions remain unanswered. The dimness of Atlas may thus remain unexplained, or partially explained, or explained through multiple competing hypotheses that cannot be definitively distinguished with available data. This ambiguity is normal in astronomy, common when observing unique objects at vast distances with finite observational resources. The comet adds one data point to the emerging understanding of interstellar visitors, a data point indicating that not all interstellar comets behave like Borisov. That diversity exists in brightness, activity, and composition among these objects, that predictions based on solar system comets may not apply cleanly to bodies formed around other stars under potentially different conditions, and the corridor forming behind the comet reflects this dimness, this lower-than-expected activity. The micrometeoroid stream will be less dense than if the comet had produced standard quantities of dust, the particle count lower, the trail fainter, though still present, still real, still spreading slowly along the hyperbolic trajectory as particles shed over weeks and months of passage disperse under radiation pressure and gravitational perturbations. The corridor inherits the comet's properties, its composition, its low activity, its origin in an unknown stellar system light-years away. Each particle in the trail is a fragment of that system, a sample delivered here by gravitational dynamics and billions of years of patient drift through the galaxy. Only took the comet's arrival to reveal its dimness, and only its departure will make that dimness final, irreversible, a fixed characteristic of this particular interstellar visitor. Unchangeable now. Part of the permanent but sparse record of objects detected from beyond, objects that passed through briefly and were observed imperfectly, objects that raised questions they could not answer, that departed leaving mysteries in their wake like the particle trails they shed, both fading gradually into the background, becoming indistinguishable from the noise, remembered only in archived data and scientific papers documenting the observations and the uncertainties and the careful, tentative conclusions drawn from insufficient information. Micrometeoroid orbits after separation begin with inheritance. Each particle receives the comet's velocity vector at the moment of separation. The comet's position and momentum transferred to the particle, establishing initial orbital elements identical or nearly identical to the parent body. But immediately, divergence begins. The particle's smaller mass means forces negligible for the comet become significant: radiation pressure, solar wind drag, electromagnetic forces. If the particle is charged, the particle's trajectory bends, slightly but measurably, away from the comet's path, beginning a slow drift that accumulates over time into substantial separation. Radiation pressure affects particles inversely with size. A particle 1 micrometer across experiences acceleration from sunlight that can exceed solar gravitational acceleration, causing the particle to spiral outward or even escape the solar system on trajectories more energetic than the comet's own hyperbolic path. A particle 100 micrometers across experiences much weaker radiation pressure. Gravity dominates, and the particle follows an orbit close to the comet's, deviating only slightly over weeks and months. Between these extremes lies a continuum, a size distribution where each size class experiences different force ratios, different accelerations, producing stratification. Smaller particles diverging faster, larger particles remaining closer to the parent trajectory. The result is a corridor with structure, with gradients, near the comet. The freshest particles cluster in compositions and sizes reflecting the current sublimation conditions. Farther back, older particles have dispersed according to their individual properties, creating layers, shells, regions where specific size classes dominate because radiation pressure has selectively accelerated or decelerated them. The corridor is not uniform, it contains texture, variation patterns that encode the history of the comet's passage. The changes in activity as solar distance decreased and then increased. the rotation of active areas creating pulses of higher and lower dust production. What remains mysterious is how long these orbital patterns persist, how quickly external perturbations randomize the particles' trajectories, erasing the structure and merging the corridor into the general interplanetary dust population. Jupiter's gravity, immense compared to the particles' tiny masses, perturbs any orbit that passes within several astronomical units of the planet. Over decades or centuries, repeated distant encounters with Jupiter, and to lesser extents with Saturn, Uranus, Neptune, will scatter particle orbits, changing their semi-major axes, eccentricities, inclinations, slowly erasing the correlation between particles that originated from the same comet. Saturn contributes additional perturbations, smaller in magnitude than Jupiter's due to lower mass and greater average distance, but still significant over long time scales. The outer planets, Uranus and Neptune, affect primarily particles whose orbits extend beyond Saturn's. Particles on the outermost fringes of the debris stream where the corridor's density is already low, where distinguishing Atlas particles from background interplanetary dust becomes difficult even before gravitational perturbations scatter them further. Only took the comet millions of years to arrive here, and only thousands of years, perhaps, for planetary perturbations to disperse its debris beyond recognition. The Poynting-Robertson effect, drag caused by the aberration of sunlight due to orbital motion, affects particles that remain gravitationally bound, causing them to spiral gradually inward toward the Sun over timescales of thousands to millions of years depending on particle size and orbital parameters. But for particles in the Tailless stream, most of which inherit the comet's hyperbolic trajectory and thus are unbound, Poynting-Robertson drag is negligible. The particles are escaping the solar system, not spiraling inward, and drag cannot reverse this fundamental trajectory characteristic. The effect applies only to the largest particles, those whose radiation pressure is weak enough that their orbits might be marginally bound, or whose near-zero excess velocity might allow Poynting-Robertson drag to eventually circularize their paths. Each particle's orbit can be described by 6 orbital elements: semi-major axis, eccentricity, inclination, longitude of ascending node, argument of perihelion, and mean anomaly. These 6 numbers completely specify the orbit's size, shape, orientation in space, and the particle's position along that orbit at any given time. For particles freshly separated from the comet, these elements are nearly identical to the comet's own orbital elements, differing only by the small velocity imparted during separation, typically a few meters per second at most, compared to the comet's 26 kilometers per second velocity relative to the Sun. But nearly identical diverges over time. Radiation pressure changes the semi-major axis and eccentricity, generally making orbits more energetic, more hyperbolic. Solar wind drag, though much weaker than radiation pressure, contributes additional perturbations. Gravitational encounters with planets alter all orbital elements randomly, depending on the geometry of each encounter. Over centuries, the tight clustering of orbital elements, the narrow range that defines the corridor as a coherent structure, will broaden, spread, eventually span ranges so wide that no clear concentration remains, no obvious grouping of particles with correlated orbits. What astronomers can calculate, given assumptions about particle size distribution, composition, and initial conditions, is the evolution of this orbital element distribution over time. Computer simulations integrate thousands or millions of particle orbits forward through time, accounting for gravity from the Sun and planets, radiation pressure, drag effects, even occasional collisions with other dust particles, though these are rare given the low particle densities. The simulations show the corridor spreading, widening, developing substructure as particles of different sizes diverge along different paths, eventually dissolving into a diffuse cloud. a statistical enhancement in particle density that becomes progressively harder to distinguish from random noise as time progresses and dispersal continues, only took physics, gravity, radiation, electromagnetism, to scatter the particles, and only time, patient, accumulating time to complete the dispersal, to erase the corridor's geometry, to randomize what was briefly organized. The time scale for complete dispersal is uncertain, spanning estimates from thousands to tens of thousands of years, depending on assumptions about particle properties and the effectiveness of various perturbation mechanisms. But the trend is unambiguous. The corridor will disperse, must disperse, cannot maintain coherence indefinitely against the randomizing forces acting on each particle. Some particles will return, in a sense, those with orbits barely hyperbolic. Those whose excess velocities are smallest might be captured by planetary encounters, scattered into elliptical orbits that remain bound to the Sun. These particles will join the solar system's permanent dust population, orbiting indefinitely or until they collide with planets, fall into the Sun, or are blown outward by radiation pressure once their orbits bring them close enough to the Sun that heating reduces their size through sublimation or fragmentation. But most Atlas particles will escape, will follow trajectories that carry them past the outer planets, past the Kuiper belt, past the heliopause where the solar wind yields to interstellar plasma, back into the interstellar medium from which the comet came. The escape process is slow. The comet itself will take thousands of years to reach the heliopause, tens of thousands more to traverse the Oort cloud if its trajectory passes through that vast spherical shell of distant comets, millions of years to travel light years from the Sun. The particles, with similar velocities, follow similar timescales. For millennia, the Atlas micrometeoroid stream will remain within the solar system, technically still part of the Sun's gravitational domain even if unbound, still subject to solar radiation and solar wind, still detectable in principle through their interactions with those solar influences. What remains uncertain is whether any Atlas particles will ever be recovered, analyzed in laboratories, subjected to the detailed compositional and isotopic measurements that reveal formation conditions and processing histories. When particles on bound orbits eventually intersect Earth's atmosphere, some survive entry heating and reach the surface as micrometeorites, particles small enough to decelerate in the upper atmosphere without melting completely, landing intact or partially intact in ice sheets, ocean sediments, desert sands. Scientists recover such micrometeorites, extract them from collected samples, analyze them under electron microscopes and mass spectrometers, determining their chemical and isotopic compositions, sometimes even their orbital origins through careful reconstruction of entry trajectories. But Atlas particles on hyperbolic orbits will not return to Earth's vicinity for centuries at minimum, possibly millennia if orbital geometries are unfavorable. And when intersections finally occur, distinguishing Atlas particles from the constant background rain of interplanetary dust will require exceptionally precise orbital measurements, tracking meteors back through their entry trajectories to determine whether their pre-entry orbits match the long-dispersed Atlas stream. The probability of recovering even a single Atlas particle, of identifying it definitively as interstellar, of analyzing its composition while knowing its origin, this probability is low, perhaps effectively zero given current recovery and analysis capabilities. So the particles will likely escape unexamined, uncollected, unanalyzed, carrying their interstellar compositions into interstellar space, samples from an unknown stellar system that passed briefly through this one and left fragments behind but left them in geometries and timescales that prevent capture, that ensure the samples remain forever unexamined except by the spectroscopic glimpses obtained during the comet's brief passage, glimpses that revealed water and carbon monoxide and dust but could not determine isotopic ratios precisely, could not measure trace elements, could not answer the detailed questions that laboratory analysis might resolve. only took one passage, one perihelion, to distribute these samples throughout the inner solar system, and only time, too much time, more time than human civilizations typically persist, will bring those samples near Earth again, assuming they are not deflected by gravitational encounters, assuming their trajectories remain calculable despite chaos and perturbations, assuming anyone is still watching when and if they return. The particles themselves remain unaware of their trajectories, their futures, their fates. They are simply matter, silicate grains, perhaps, or carbonaceous aggregates, or mixtures of minerals and organics, possibly still containing traces of water ice in their interiors if they are large enough that solar heating has not yet penetrated to their cores. Each particle continues following its orbit, its path through space determined entirely by forces acting upon it, gravity pulling it into curved trajectories around the sun, radiation pressure pushing it outward, solar wind plasma perhaps eroding its surface atoms molecule by molecule, cosmic rays occasionally striking and depositing energy but producing no macroscopic effects on trajectory or structure. The corridor they collectively form is mathematical, not physical in any tangible sense. No boundary marks where the corridor begins or ends, no surface defines its edges. It exists as a probability distribution, a region of space where the likelihood of encountering an Tailless particle is elevated compared to adjacent regions, elevated by factors that might be 2, 10, perhaps 100 in the densest parts of the stream shortly after the comet's passage. But even at peak density, the corridor remains sparse, perhaps 1 particle per cubic kilometer, perhaps 1 per 1,000 cubic kilometers, estimates that carry enormous uncertainties and depend entirely on assumptions about total mass shed and size distribution. To traverse the corridor, to fly a spacecraft through it, would reveal nothing to the unaided eye or to optical cameras. The particles are too small, too dark, too dispersed. They do not reflect enough sunlight to be visible as stars or even as faint nebulosity. A spacecraft might detect them through impacts on dust detectors, sensors that register the tiny plasma flashes created when particles strike at high relative velocities, or through collected samples if the spacecraft carried aerogel or other capture media. But without such specialized instruments, the corridor would be invisible, indistinguishable from empty space, its presence revealed only through statistics, through counting impacts over time and comparing rates to background levels, through integrating measurements over large volumes and long durations to detect the slight enhancement indicating passage through a debris stream. What the corridor does encode, in the collective orbits of its constituent particles, is information about the comet's trajectory, about the timing and intensity of its activity, about the forces acting on particles of different sizes. This information is written in orbital elements, in the spatial distribution of particles, in the correlations between position and velocity that distinguish stream particles from randomly distributed background dust. Reconstructing this information requires observing many particles, measuring their orbits individually, identifying the patterns that reveal common origin. Such reconstruction has been performed for meteor streams associated with periodic comets, streams that Earth intersects annually or periodically, producing predictable meteor showers that allow systematic observation and orbit determination. But for Tailless, no such systematic observation will occur. Earth does not intersect the stream. No meteor shower will mark the comet's passage. No annual reminder will occur. No Perseids or Leonids or Geminids derived from Tailless debris. The corridor will remain unobserved, its particles counted only in theoretical estimates, its structure mapped only in computer simulations, its information content preserved only in orbital mechanics but never read by observers, never decoded into detailed understanding of the comet's behavior or history. Only took one comet to create this corridor, And only the absence of intersecting geometry, the orbital plane mismatch, the timing that places Earth elsewhere when particles arrive, the sheer vastness of space that makes encounters improbable, to ensure the corridor remains observationally invisible despite its physical existence, despite the millions of particles it contains, despite the information encoded in their trajectories about processes that occurred when the comet passed through the inner solar system shedding mass, creating this trail that will persist for millennia before dispersing completely. The particles drift outward. Those smallest and most affected by radiation pressure lead the way, traveling fastest, accumulating the most distance from the Sun. Those largest and least affected follow more closely to the comet's own trajectory, lagging behind as the comet's nucleus, still sublimating, still shedding mass, still creating new particles, continues outward at its steady hyperbolic pace. The corridor lengthens, stretches, becomes an ever thinner ribbon of dust extending from the comet's perihelion position, where the earliest particles were shed, to its current position beyond Mars's orbit and climbing, a ribbon that will eventually extend across astronomical units. Tens of astronomical units, eventually hundreds as the comet and its oldest particles recede toward the outer solar system's edge. What remains predictable is the corridor's ultimate fate: dispersal, dissolution, merging with the background. The particles will scatter, their orbits randomized by perturbations, their spatial distribution broadened until no concentration remains, until the probability of encountering an Tailless particle anywhere in the inner solar system falls to levels indistinguishable from the probability of encountering any random interplanetary dust grain. The corridor will cease to exist as a distinct structure, will become instead a slight elevation in the general dust density, an elevation so small it might never be detected, never be confirmed, never be distinguished from statistical noise in the measurements of interplanetary dust flux. And then, eventually, the particles themselves will leave. Those on hyperbolic trajectories will cross the heliopause, will enter the interstellar medium, will become interstellar dust once again, dust that originated in one stellar system, traveled for millions or billions of years through interstellar space as part of a comet, briefly passed through this stellar system, briefly experienced solar heating and planetary gravity, and now returns to interstellar space carrying atoms and molecules from the comet's birth disk, unchanged in composition, barely changed in structure despite the journey, ready to drift for millions more years until perhaps encountering another star, another system, continuing the slow exchange of matter between stellar systems that has occurred throughout galactic history. That will continue as long as stars form and planets eject comets, and comets wander between the stars. Only took gravity and radiation and time to set these particles on their paths, and only more time, vastly more time than has elapsed since the comet's arrival, will complete their journeys, will carry them light years from here, will disperse them so thoroughly that even their common origin becomes unrecognizable, becomes erased by the randomizing forces of galactic dynamics, by encounters with molecular clouds and spiral density waves and other stars' gravity, until nothing remains of the corridor except the particles themselves, scattered and separated, each following its own trajectory through a galaxy containing hundreds of billions of stars and presumably trillions or quadrillions of comet-derived dust particles, all mixing, all drifting, all carrying the compositions of their parent systems, but carrying no markers of identity, no labels, no way to determine which particles came from which comets, from which stars, except through detailed compositional analysis that might, in principle, match isotopic signatures to stellar nucleosynthesis patterns, but which in practice remains beyond current capabilities and may remain so indefinitely. What happens when they enter Earth's atmosphere begins with velocity. The particles, if any ever intersect Earth's orbit, will arrive at speeds determined by the combination of Earth's orbital velocity around the Sun and their own hyperbolic velocities. Earth orbits at roughly 30 kilometers per second. The Tailless particles move at their inherited velocity from the comet, perhaps 20 to 30 kilometers per second relative to the Sun, but in a different direction, creating relative velocities at Earth encounter that could range from 20 kilometers per second if the particles approach from behind Earth in its orbit, to 80 kilometers per second if they approach head-on. These are the highest meteor velocities possible in the solar system. Only interstellar particles can achieve such speeds. Bound solar system objects being limited by orbital mechanics to lower relative velocities at Earth encounter, at 70 or 80 kilometers per second, atmospheric entry is violent. The particle, assume 110 micrometers across, a typical micrometeoroid, strikes air molecules in the upper atmosphere at altitudes around 100 to 120 kilometers, where atmospheric density is roughly 1/1,000,000th of sea level density, but still sufficient to interact with the incoming particle. Each collision between the particle and an air molecule transfers kinetic energy. The particle's enormous velocity means enormous kinetic energy despite its tiny mass. A 10 micrometer particle moving at 70 kilometers per second carries kinetic energy measured in microjoules, but this energy is deposited into a volume measured in cubic micrometers, creating temperatures that instantaneously reach thousands of Kelvin. The particle heats, its surface layer ablates, atoms and molecules boiling away, stripped off by the intense heating. The ablated material ionizes. Electrons stripped from atoms by temperatures exceeding 10,000 Kelvin, creating a small plasma cloud that glows, emitting visible light. This is meteoric emission, the light from meteors, from shooting stars. Though at micrometeoroid scales the emission is far too faint for human eyes to detect. Larger meteoroids, millimeter to centimeter scale, produce meteors bright enough to see, sometimes bright enough to cast shadows, trails of ionized gas marking their paths through the upper atmosphere. But micrometeorites produce only faint glows detectable by sensitive instruments, cameras with long exposures, radar systems that reflect radio waves off the ionized trails. What remains uncertain for interstellar particles is whether they survive entry or ablate completely. Survival depends on the balance between kinetic energy and mass. Larger particles carry more mass relative to their surface area, can absorb more total heating before their entire volume reaches ablation temperature. Smaller particles have higher surface area to mass ratios, heat through quickly, ablate completely, leaving no solid remnant. The transition size, the approximate diameter above which particles survive and below which they ablate, depends on velocity, composition, entry angle, atmospheric conditions. For typical solar system particles entering at 40 to 50 kilometers per second, the survival threshold lies around 20 to 50 micrometers. For interstellar particles entering at 70 to 80 kilometers per second, the threshold might be higher, perhaps 100 micrometers. Though uncertainties are large, most Tailless particles, being smaller than 100 micrometers, would ablate completely if they entered Earth's atmosphere. Their atoms would disperse in the mesosphere, mixing with atmospheric gases, oxidizing, eventually settling through the stratosphere and troposphere over years or decades, reaching the surface as components of rain or snow or dry deposition, indistinguishable from terrestrial atoms or atoms from ordinary interplanetary dust. Only the largest Tailless particles, rare, uncertain in existence, perhaps not present at all in the debris stream, might survive entry, might reach the surface as partially melted or unmelted fragments collectible as micrometeorites. The collection of micrometeorites occurs in locations where terrestrial contamination is minimal: Antarctic ice, Greenland ice, deep-sea sediments, high-altitude atmospheric dust samples. Scientists melt ice or filter sediments, extract the small dark particles that do not match terrestrial geology, examine them under microscopes, analyze their compositions. Most micrometeorites are solar system objects, fragments from asteroids or comets on bound orbits. But distinguishing bound from unbound, solar system from interstellar, requires orbital information rarely available for such small particles. Only if an Tailless particle entry were observed, its trajectory measured by multiple cameras or radar stations, its pre-entry orbit calculated, its hyperbolic nature confirmed, could its interstellar origin be definitively established. But micrometeorites are too small and faint to produce observable meteors in most cases. Their plasma trails are too dim, their passage too brief, their spatial density too low for systematic observation networks to detect more than a tiny fraction of entries. The probability of both observing an Tailless particle entry and recovering the meteorite, if any survives, is vanishingly small, perhaps effectively zero given current observational capabilities and the rarity of large particles in the Tailless stream. What the entry would reveal, if observed, is information about the particle's composition through spectroscopic analysis of the emission from its plasma trail. Different elements emit at different wavelengths when ionized and excited. The spectrum of a meteor's light encodes its composition, revealing whether it contains primarily silicates, iron, organic compounds, or mixtures. Interstellar particles might show compositional anomalies, unusual ratios of elements, different mineral forms, organic compounds not found in solar system meteorites, though the Tailless comet spectroscopy suggested composition similar to solar system comets, implying its dust might also resemble solar system dust in most properties. The isotopic composition, the ratios of different isotopes of elements like hydrogen, carbon, oxygen, would provide more definitive evidence of interstellar origin. But isotopic measurements require laboratory analysis of recovered samples, not just spectroscopy of atmospheric emissions. A surviving Tailless micrometeorite, analyzed for isotopes, might show deuterium to hydrogen ratios or oxygen isotope patterns inconsistent with solar system formation, revealing its extrasolar origin. Or it might show ratios indistinguishable from solar system values, suggesting either that its parent system had similar isotopic compositions or that entry heating and atmospheric interaction modified the isotopes, erasing the original signatures. Only took one atmospheric entry, hypothetical and unlikely, to reveal how difficult confirming interstellar dust in Earth's collection of extraterrestrial samples actually is, requiring not just survival of entry, not just recovery of the particle, not just analysis of composition and isotopes, but also orbital confirmation of hyperbolic trajectory, correlation with known interstellar objects, and measurements precise enough to distinguish interstellar signatures from the noise of terrestrial contamination and solar system background. The barriers are numerous, the probabilities low, the requirements stringent. Yet micrometeorites do reach Earth constantly, particles from bound orbits entering the atmosphere at rates of roughly 40,000 tons per year, mostly particles smaller than 100 micrometers, most ablating completely but some surviving, accumulating on the surface as a slow rain of extraterrestrial material. Among this constant flux, interstellar particles may occasionally arrive, perhaps a few particles per year from all interstellar sources combined, given estimates of interstellar comet frequency and debris production. But identifying these rare interstellar grains among the overwhelming majority of solar system particles remains beyond current capabilities, may remain so until technology advances to allow systematic orbital tracking of micrometeoroid entries or until recovery methods improve to collect and analyze millions of particles, searching for the rare anomalies that indicate extrasolar origin. What is certain is that the exchange occurs, has occurred, will continue occurring. Interstellar dust enters the solar system constantly, carried by passing comets like Atlas, by asteroidal objects like Oumuamua if it shed any debris, by the ambient flow of interstellar dust that the solar system plows through as it orbits the galaxy. Some fraction of this dust, small but non-zero, eventually spirals inward through radiation pressure or gravitational perturbations, reaches the inner solar system, intersects planetary orbits, enters atmospheres. Earth has been accumulating interstellar dust throughout its history, since its formation 4.5 billion years ago, likely accreting small amounts with every interstellar visitor that passed nearby. Every debris stream that Earth's orbit happened to intersect. The accumulated mass is negligible, perhaps a few tens or hundreds of kilograms over Earth's entire history, an amount invisible against the billions of tons of solar system meteoritic material accreted over the same period. But the significance exceeds the mass. Each interstellar grain is a sample from another stellar system, evidence of planet formation and comet ejection processes occurring around other stars, potential carrier of prebiotic molecules or isotopic anomalies or mineral forms that reveal different formation conditions. The grains are data, information, physical evidence of the galaxy's diversity and the universal processes that govern star and planet formation. Only took atmospheric entry to bring these samples to Earth's surface, and only the difficulty of identification. The overwhelming background of similar-appearing solar system material. The lack of definitive markers distinguishing interstellar from native grains. Only these obstacles prevent their systematic study, their contribution to understanding planet formation throughout the galaxy, their revelation of whether Earth's formation was typical or unusual, whether the solar system's composition represents galactic norms or local variations. The answers likely exist, scattered across Earth's surface in the form of unrecognized interstellar micrometeorites, waiting for identification methods that can find them among millions of solar system grains, can confirm their origins, can extract their information about formation conditions light years away and billions of years ago, encoded in atomic arrangements and isotopic ratios that survive entry heating and preserve records of their parent systems. The slow dispersal of the trail begins immediately. From the first moment each particle separates from the nucleus, dispersal is inevitable, written into the physics governing particle motion through space. Gravity, radiation, collisions, perturbations, all acting constantly to randomize what begins as organized, to spread what begins as concentrated, to dissolve structure into entropy. The corridor is temporary, its coherence a brief state maintained only while the particles remain freshly shed, their orbits still tightly clustered, their spatial distribution still reflecting the comet's passage. Time erodes this coherence, slowly but irreversibly, expanding the corridor's width, lengthening its extent, reducing its peak density until eventually no concentration remains detectable above background. The widening occurs laterally, perpendicular to the mean trajectory. Particles with different sizes experience different forces. Radiation pressure accelerates smaller particles more than larger ones, creating velocity differences measured in centimeters or meters per second. These seem negligible, but integrated over years they accumulate into kilometers of separation, over decades into hundreds of thousands of kilometers, over centuries into spatial distributions so broad that adjacent particles shed minutes apart from adjacent locations on the nucleus, find themselves separated by distances exceeding Earth's diameter. Gravitational perturbations contribute additional spreading, particularly when particles pass near planets. A particle passing within Jupiter's Hill sphere, the region where Jupiter's gravity dominates over the Sun's, experiences trajectory changes that depend sensitively on the exact distance and geometry of closest approach. Two particles on nearly identical orbits, differing in position by mere kilometers when they reach Jupiter's vicinity, might exit the encounter on substantially different trajectories, their orbital elements diverging by amounts that translate into millions of kilometers of separation at later times. This is chaotic dynamics. Sensitive dependence on initial conditions. the mathematical signature of systems where tiny differences grow exponentially rather than linearly. What remains mysterious is the exact rate of dispersal, the timescale over which the Tailless corridor will lose coherence. Models provide estimates, but estimates depend on assumptions about particle size distribution, about how many particles pass near which planets, about the effectiveness of radiation pressure at different solar distances, about collision rates with background interplanetary dust. Different assumptions produce different timescales, ranging from centuries to tens of millennia. The truth likely falls somewhere in this range, but pinning it down requires observations that will never occur, tracking individual particles over centuries, mapping the corridor's evolution, measuring widening rates directly. The lengthening of the trail is more predictable. Particles shed early, near perihelion when sublimation was most intense, have now traveled farther along their trajectories than particles shed later. The corridor thus extends from the comet's perihelion position, where it was weeks or months ago, to its current position and beyond. If any particles were shed before discovery, before the comet brightened enough for detection, this length increases linearly with time, simply because particles maintain their velocities, continue moving along their individual paths, spreading out along the trajectory like a column of soldiers marching with slightly different speeds, gradually stretching from tight formation into extended line. But the line is not straight. Each particle's trajectory curves under solar gravity, and different sizes curve differently due to radiation pressure. The corridor develops three-dimensional structure, a ribbon that twists through space, broad in some directions and narrow in others, with thickness and width determined by the distribution of perturbations, the range of forces acting on particles of different properties. Mapping this structure would require observing the corridor from multiple vantage points, triangulating particle positions, constructing three-dimensional models of density distributions. No such observations exist. The corridor remains mapped only in computer simulations, only in theoretical reconstructions based on assumed initial conditions and integrated trajectories. Only took months for the comet to shed the particles forming the corridor, and millennia will be required to disperse them completely. A temporal asymmetry reflecting the ease of creating structure compared to the difficulty of maintaining it against thermodynamic and dynamical randomization. The universe favors disorder, increases entropy, spreads concentrated energy and matter into diffuse distributions that approach equilibrium. The corridor fights this trend briefly through its gravitational organization, its correlated particle orbits, but cannot resist indefinitely. Entropy wins eventually, always, inexorably. The dispersal is not uniform. Some regions of the corridor, regions where particle density was initially highest, where the comet's activity peaked, will remain coherent longer, their enhanced density surviving even as lower density regions fade into background. These high-density cores might persist as recognizable enhancements for thousands of years, identifiable through careful statistical analysis of micrometeoroid flux even after the corridor as a whole has dispersed beyond obvious detection. But, eventually, even these cores will spread, their particles scattered by accumulated perturbations, their distinctiveness erased. Collisions among particles contribute minimally to dispersal at the densities characteristic of the Tailless corridor, even in the densest regions. Particle spacing averages thousands of kilometers, and relative velocities between particles are small, meters per second at most. Since all particles share similar orbital velocities, collision rates are correspondingly low, perhaps one collision per particle per million years, insufficient to significantly affect the corridor's evolution over timescales of mere centuries or millennia. Collisions with background interplanetary dust are slightly more frequent but still rare, and most collisions at these velocities do not destroy particles, merely chip them, erode surfaces, slowly reduce sizes over million-year timescales. What does affect individual particles is solar heating, particularly for particles on orbits that bring them close to the Sun. Radiation intensity increases inversely with the square of solar distance. A particle at 1 astronomical unit receives 4 times the radiation of a particle at 2 astronomical units, 16 times the radiation at 4 astronomical units. For particles small enough, this heating can sublimate remaining volatile compounds, can drive off water ice if any persists in particle interiors, can even break down complex organic molecules into simpler compounds that then evaporate. The heating alters particle properties, mass, composition, optical characteristics, which in turn affects how radiation pressure acts, creating feedback loops where heating changes particle responses to the forces driving dispersal. The timescale for complete volatile loss from small particles is short, perhaps years to decades at 1 astronomical unit, longer at greater distances. Most Tailless particles will lose any remaining volatiles within a century of separation from the nucleus, becoming purely refractory, silicates, organics, perhaps some metals, all compounds stable at solar system temperatures. These refractory remnants continue orbiting, continue dispersing, but no longer evolve compositionally. Having reached equilibrium with the solar radiation environment, only took solar heating to drive the sublimation that created the particles initially, and more solar heating now modifies the particles, completing their transformation from fragments of an icy comet into refractory dust grains indistinguishable, in most respects, from other interplanetary dust particles. The transformation erases volatiles, erases some of the compositional information that might identify the particles as interstellar, though refractory components, the silicates and organics that do not sublime, preserve isotopic ratios and mineralogical signatures that might still reveal extrasolar origin if ever analyzed. The corridor will eventually intersect nothing, affect nothing, pass through the inner solar system, leaving no observable consequences. Earth's orbit and the corridor's geometry do not align. No meteor shower will result. No annual display of interstellar meteors. Other planets might intersect the corridor, Mars, Venus, Mercury, perhaps even gas giants if particles' perturbed orbits bring them outward, but at such low particle densities. Intersections are rare. Perhaps one particle encountering a planet's atmosphere per year across all planets combined. Events too infrequent to produce observable effects. Too scattered to allow systematic study. What remains of the corridor after millennia is mathematics, the equations describing particle trajectories, the simulations predicting dispersal, the archived observations documenting the comet's passage and gas production and dust emission. These records preserve the corridor's existence, its properties, its place in the catalogue of interstellar object debris streams. Future astronomers, if they access these archives, will know the corridor formed, will be able to calculate where particles should be at any given time, will potentially identify intersections with spacecraft trajectories or planetary orbits. But without such calculations, without deliberate searches, the corridor itself, the physical distribution of particles, will remain invisible, undetected, known only through inference and simulation. Only took one comet's passage to create this corridor, this temporary structure, this geometric pattern of particle trajectories that will gradually dissolve into the background noise of interplanetary dust, becoming indistinguishable within millennia, remembered only in databases and scientific publications. Physical evidence of the corridor lost to dispersal. Its particles scattered so thoroughly that reconstructing their common origin becomes impossible without detailed compositional analysis of each particle individually. Analysis unlikely to occur for dust grains so small, so dark, so dispersed across cubic astronomical units of space. The corridor fades. Not visibly, it was never visible, but statistically, Mathematically, geometrically, the enhancement in particle density decreases. The correlation between particle orbits weakens. The structure that briefly existed, that encoded information about the comet's passage, that traced the hyperbolic trajectory through three-dimensional space, this structure dissolves, erases itself through the accumulated effect of small perturbations acting over long times, leaving only isolated particles on randomized orbits, each carrying its composition, its interstellar origin, its journey from another star, but carrying no connection to the other particles. No sign of common ancestry except in atomic arrangements too subtle to detect without laboratory analysis that will likely never occur. Calculating the return that will never come begins with orbital mechanics, with the mathematics of hyperbolic trajectories, with the fundamental relationship between velocity and gravitational potential energy that determines whether an object is bound or unbound to a central mass. For 3I/Tailless, the calculation is straightforward. Measure the comet's velocity vector at any point along its trajectory. Measure its distance from the Sun. Calculate the total orbital energy, kinetic plus potential, and check the sign. Positive energy means hyperbolic, means unbound, means the comet will escape to infinity and never return. The measurements confirm energy is positive, substantially positive. Leaving no ambiguity, no possibility that measurement uncertainties might shift the result into negative territory. The eccentricity provides another confirmation. Orbits with eccentricity less than 1 are ellipses, closed curves, bound trajectories. Eccentricity equal to 1 defines a parabola. The boundary case between bound and unbound, requiring infinite time to escape to infinite distance. Eccentricity greater than 1 describes a hyperbola, an open curve, an escape trajectory for Tailless. Eccentricity measures approximately 1.4, significantly hyperbolic, indicating the comet will asymptotically approach a final velocity, its hyperbolic excess velocity, far from the Sun where gravitational potential energy approaches 0 and kinetic energy equals the total orbital energy. This final velocity is roughly 26 kilometers per second relative to the Sun, measured in the Sun's rest frame. But the Sun is not at rest. It orbits the galactic center at approximately 220 kilometers per second, much faster than the comet's escape velocity. The comet's trajectory through the galaxy thus combines its velocity relative to the Sun with the Sun's galactic orbital velocity, producing a complex path through the galactic disk that curves, wobbles, rises and falls through the disk's vertical structure as it participates in the general galactic rotation, while also maintaining its peculiar velocity inherited from the ejection event that created its interstellar trajectory. What remains uncertain is where exactly the comet will travel over the millions of years following its departure from the solar system. The trajectory points currently toward Ursa Major, roughly toward the constellation's direction in the sky. But this direction is only approximate, constellations being two-dimensional projections of three-dimensional space, stars at vastly different distances creating illusory groupings. The comet's actual three-dimensional velocity vector points toward a specific direction in galactic coordinates, a direction determined by its velocity components in galactic latitude and longitude, its motion perpendicular and parallel to the galactic plane. Integrating this trajectory forward through time requires modeling the galaxy's gravitational field, accounting for the mass distribution in the galactic disk, the bulge, the dark matter halo. The galaxy's gravity is not